For all our dreams of travelling into deep space, humanity may be far more limited than we want to accept. Rockets launch, satellites operate, and telescopes capture the faint light of distant planets. Yet each advancement in space exploration exposes a difficult fact. Most of the universe is incompatible with human life. It is filled with radiation, extreme temperatures, unstable environments, and conditions that no unprotected organism can survive. Science fiction often presents starships and successful colonies on distant worlds, but actual research continues to reveal overwhelming barriers. So, do humans have the ability to survive beyond Earth? And what are the limits of human progress in a universe that offers very few places where we can actually live? The environment beyond Earth is often described as mysterious, silent, and beautiful, but the deeper truth is far less forgiving. The space beyond our atmosphere is not an extension of the peaceful night sky we see from the ground. It is a region filled with dangers that human biology was never designed to handle. When we look up at the stars, we see calm lights sprinkled across a black background, but when scientists describe what actually fills that blackness, their words paint a picture that is harsh, violent, and extremely threatening to life as we know it. Deep space is full of intense radiation, absolute vacuum, extreme temperatures that swing between deadly heat and deadly cold, and an environment where even the smallest mistake can lead to disaster within seconds. The more we study space, the more clear it becomes that humans evolved inside the protective bubble of Earth, and once we step outside that bubble, everything we take for granted disappears instantly. It is easy to forget how special Earth's environment is. Our planet is wrapped in a thick atmosphere made of nitrogen, oxygen, and small amounts of other gases, and this atmosphere protects us from radiation, slows down dangerous space debris, and maintains temperatures that allow liquid water to exist. Above the atmosphere is a powerful layer called the magnetosphere, created by the movement of molten iron in Earth's core. This magnetosphere acts like a giant shield, redirecting harmful charged particles from the Sun and from beyond the solar system. Without these two layers, the atmosphere and the magnetosphere, life on Earth would be bombarded every second by invisible forms of energy that would damage cells, break DNA, and eventually kill any living thing that was exposed for too long. When astronauts leave Earth, even if they are in low orbit, they leave behind this natural protection. However, the International Space Station, which orbits roughly 400 kilometers above Earth's surface, is still inside the magnetosphere. Astronauts there experience higher radiation than we do on the ground, but the level is still manageable with protective shielding and limited exposure. The real danger begins when humans travel beyond low Earth orbit, into regions where Earth's magnetic field no longer offers protection. The moment a spacecraft crosses that invisible boundary, it enters a universe that has never been friendly to biological life. One of the main threats in deep space is radiation, which in space comes in three main forms. The first form is solar radiation, also called solar energetic particles. These are high-energy particles, mostly protons, that are constantly emitted by the Sun. Most of the time, the Sun releases a steady flow of these particles in what is called the solar wind. But occasionally, the Sun erupts with massive bursts called solar flares or coronal mass ejections, which can accelerate particles to extremely high energies. These events can occur in less than 1 second, with no warning, and send powerful radiation storms across the solar system. The second form of radiation is called galactic cosmic rays. These particles come from outside our solar system, launched at nearly the speed of light from exploding stars or from other violent events in the galaxy. Galactic cosmic rays are far more energetic than solar radiation. Some of them have so much energy that no machine built on Earth can replicate it. Their energy is high enough to slice through metal, electronics, and human tissue with ease. A single cosmic ray can pass through an astronaut's body, destroy the DNA inside multiple cells, and cause long-term health problems, including cancer, cataracts, or radiation sickness. The third form of radiation comes from the spacecraft itself. When high-energy cosmic rays hit the metal walls of a spacecraft, they can generate secondary particles. These particles are created when cosmic rays collide with atoms in the spacecraft structure, causing smaller particles such as neutrons, electrons, and gamma rays to scatter inside the spacecraft. This means that even if you shield against cosmic rays, the shield can create a new type of radiation inside the spacecraft, which also damages human tissue. Radiation in deep space is measured in units called sieverts, which tell us how much biological damage radiation can cause. On Earth, people are usually exposed to only a few thousandths of a sievert each year, which is safe. But astronauts travelling in deep space could be exposed to 1 full sievert or more within a single long mission. Long-term exposure to 1 sievert increases the risk of fatal cancer by a large percentage. Exposure to 2 or 3 sieverts can cause severe damage to blood cells, the immune system, and organs. Exposure to 10 sieverts in a short time is enough to kill a human within weeks. In deep space, some solar events can deliver several sieverts of radiation in less than 1 hour. Without thick shielding, which itself is extremely heavy and expensive to launch, astronauts would be in immediate danger. Another danger of deep space is the vacuum. On Earth, we live under pressure from the atmosphere. When you breathe in, oxygen enters your lungs because air is pushing against your body. In space, there is no air pressure and nothing pushes against the body. If a person were suddenly exposed to vacuum without a suit, the air inside their lungs would rush out instantly, causing lung damage. Water and bodily fluids would begin to boil at normal body temperature because there is no pressure to keep them in liquid form. Contrary to popular belief, the body would not explode, but it would swell, and the person would lose consciousness in less than 15 seconds because oxygen could no longer enter the bloodstream. Brain death would follow within minutes. Even with a spacesuit, the vacuum of space creates constant challenges. Spacesuits must maintain pressure on the body, supply oxygen, remove carbon dioxide, regulate temperature, and protect against radiation. They must do all of this while allowing movement. Designing such a suit is extremely difficult, which is why spacesuits are bulky, heavy, and hard to move in. When astronauts perform spacewalks near the International Space Station, they depend entirely on life support systems built into their suits. A small tear, a malfunctioning regulator, or even a sharp piece of space debris could be deadly almost instantly. Temperature is another major threat in deep space. Many people believe space is cold, but the truth is more complicated. Space has no air, and heat moves in 3 ways: conduction, convection, and radiation. In space, conduction and convection do not work because there is no air or matter for heat to move through. Therefore, objects in space heat up or cool down only through radiation. When an object is in direct sunlight, it absorbs energy from the sun and can heat up very quickly. When it is in shadow, it releases heat into space and becomes extremely cold. Temperatures can swing hundreds of degrees, ranging from below -150 degrees Celsius to above 120 degrees Celsius. These temperature swings can damage equipment, crack surfaces, and make it impossible for the human body to stay alive without advanced thermal control systems. In deep space, a spacecraft must constantly regulate its temperature. Engineers must design surfaces that reflect sunlight, absorb it only where necessary, and radiate heat away from the spacecraft when it gets too hot. Without these systems, the interior of the spacecraft would either freeze or overheat. The human body can only survive in a narrow temperature range, and even a few degrees above or below normal body temperature can cause serious medical problems. Space leaves no room for error. Another danger in deep space comes from tiny pieces of debris. On Earth, dust is harmless, but in space, a grain of dust travelling at tens of thousands of kilometers per hour becomes a deadly projectile. Because there is no air resistance in space, objects can travel at extremely high speeds without slowing down. Space debris, meteoroids, and microparticles strike spacecraft constantly. Most of them are so small that they do no damage, but some are large enough to puncture surfaces, crack windows, or destroy key systems. Engineers design spacecraft with multiple layers of shielding to absorb impacts, but no protection is perfect. The threat of high-speed collisions exists every second in deep space. The distance involved in deep space travel also creates enormous challenges. On Earth, help is always close. Even in low Earth orbit, astronauts on the International Space Station can return to Earth in a matter of hours. But once a spacecraft travels farther away, returning becomes impossible without planning, fuel, and functioning systems. For example, when astronauts traveled to the Moon in the late 1960s and early 1970s, they were roughly 400,000 kilometers away from Earth. At that distance, communication delays are only a couple of seconds, and the spacecraft could return in a few days if necessary. But traveling to Mars is a completely different situation. At its closest, Mars is 55 million kilometers from Earth. At its farthest, it is more than 400 million kilometers away. A mission to Mars would take many months one way, and the astronauts would be completely isolated. If something goes wrong on a Mars mission or any deep space mission, there is no quick rescue. If a system fails, astronauts must repair it themselves. If radiation levels spike due to a solar storm, they must rely on whatever shielding they brought with them. If someone becomes seriously ill, the spacecraft cannot turn around. Deep space makes humans profoundly vulnerable. Human psychology is also affected by deep space conditions. Humans are social creatures who evolved to live in communities, surrounded by changing environments, natural light cycles, and physical space to move around. In deep space, astronauts would be confined to a small spacecraft for months or years. The lack of sunlight, the absence of natural scenery, and the constant awareness that death is only a thin metal wall away creates psychological stress that can increase over time. Scientists study these effects on Earth by placing volunteers in sealed habitats for months, and the results show that isolation, monotony, sleep disruption, and interpersonal conflict are constant problems. These psychological challenges are just as real as physical dangers. Another issue is the effect of weightlessness on the human body. In deep space, far from any planet, astronauts experience microgravity. Without gravity, the body begins to change. Muscles weaken because they no longer support body weight. Bones lose density because the body no longer needs to keep them strong. Astronauts on long missions can lose up to 1/5 of their bone mass within months if they do not exercise intensely every day. The heart becomes weaker because it no longer needs to push blood upward against gravity. Body fluids shift toward the head, causing pressure that can damage the eyes and lead to long-term vision problems. Even the immune system weakens in microgravity, making astronauts more vulnerable to infections. When astronauts return to Earth after months in microgravity, they often struggle to stand or walk. Some experience difficulty balancing, dizziness, and fainting. If humans were to spend years in deep space, these effects would become more severe. The question becomes how to keep the body strong when gravity is absent. Scientists have proposed spinning spacecraft to create artificial gravity, but this requires large structures that are difficult to build and launch. As of today, no spacecraft capable of generating artificial gravity has ever been built for human use. Food and water present another challenge. Humans need clean water and balanced nutrition to survive. On Earth, water is abundant and food can be grown easily. In deep space, everything must be carried from Earth or recycled. The International Space Station recycles most of its water from urine, sweat, and humidity. The system is not perfect, and it requires constant maintenance. Growing food in space is extremely difficult because plants rely on gravity to guide their roots downward and their stems upward. In microgravity, roots grow in random directions, water does not flow naturally, and soil behaves strangely. Scientists have grown small plants in orbit, but producing enough food to feed astronauts for years remains a major challenge. Another issue is the need for oxygen. Humans need oxygen every second, but oxygen is not easy to store or produce in space. On Earth, plants create oxygen through photosynthesis, but maintaining large, healthy plant systems in space requires light, water, nutrients, and stable conditions, all of which are hard to provide. Spacecraft carry oxygen tanks and also produce oxygen by splitting water molecules using electricity. If this system fails, oxygen levels drop quickly. Space also presents engineering challenges that do not exist on Earth. Electronics behave differently under radiation. High-energy particles can strike a microchip and flip a single bit of data, causing errors that may lead to software failure. This is called a single-event upset. A single cosmic ray can disable a computer, shut down a system, or corrupt important data. Engineers create radiation-hardened electronics, but these are expensive and slow compared to ordinary electronics. Even with shielding, no system is completely safe. Communication also becomes more difficult the farther humans travel. Radio signals move at the speed of light, but when distances stretch into tens of millions of kilometers, delays become unavoidable. A message sent from Mars to Earth can take between 3 minutes and more than 20 minutes one way. This makes real-time communication impossible. Astronauts must make decisions without waiting for instructions, increasing the risk during emergencies. Then there is the danger of long-term exposure to the deep space environment. Even tiny doses of radiation absorbed daily accumulate over time. DNA damage builds up in cells, mutations increase, the risk of cancer grows, vision issues worsen, the immune system weakens, the body becomes more fragile. The limits of human physiology become clearer every time we try to understand what prolonged life beyond Earth does to the human body and brain. Even though humans have dreamed for centuries of living among the stars, the truth is that the universe exposes the body to forces and conditions that it was never shaped to handle. Human biology evolved over billions of years under the pull of Earth's gravity, under the protection of Earth's magnetic field, and within the comfort of Earth's atmosphere. The moment a person leaves this environment, every system inside the body must work harder than it was designed to, and many of those systems begin to break down in slow, dangerous, and sometimes invisible ways. When people talk about travelling to distant planets, they often think of rockets, engines, and technology. But the far greater challenge comes from what happens inside the human body itself when it is exposed to microgravity, cosmic radiation, and long periods of isolation. Microgravity changes the body from the very first minute a person enters orbit. On Earth, the body's always fighting gravity. Muscles grow strong because they constantly support weight. Bones remain dense because they carry loads. Blood flows downward because gravity pulls it, and the heart must pump harder to send blood upward again. But in microgravity, which is the environment astronauts experience in space, there is almost no pull on the body. Everything floats, including the organs, the fluids, and the skeleton itself. In only a few hours, the blood inside the body shifts upward because there is no force pulling it down. This makes the face puffier, the eyes feel pressure, and the brain work differently. The heart does not need to beat as hard to move blood, so it begins to weaken. The muscles of the legs no longer carry weight, so they begin to shrink. The bones stop getting the signal that they must stay strong, so they start to lose minerals like calcium. Scientists have measured that astronauts can lose up to 1% of bone mass every single month they spend in microgravity, which is extremely rapid compared to bone loss on Earth. This means that after 1 year in orbit, a person can return with bones that are significantly weaker and more prone to breaks. The spine also changes because gravity no longer compresses it. The soft discs between the vertebrae expand, and the spine stretches upward. This makes astronauts grow taller by several centimeters, but it also causes back pain and increases the risk of spinal problems later in life. Without gravity pushing organs downward, they shift position slightly. The stomach, intestines, and other organs move in ways that are not harmful at first, but the long-term effects are still not fully understood. Even the vestibular system inside the inner ear, which helps a person balance, becomes confused because it no longer senses the direction of down. This causes nausea, dizziness, and motion sickness for the first few days in space. The muscles weaken very quickly because they no longer need to work. Even with 2 hours of exercise every day, astronauts still lose muscle mass. The muscles that help a person stand, walk, lift, and stabilize their body grow smaller and softer. When an astronaut returns to Earth after months in space, simple tasks like walking, standing, or lifting objects become difficult. Some astronauts faint because their cardiovascular system is no longer used to pushing blood upward against gravity. Others struggle to keep their balance because their inner ear and brain need time to relearn how to move in a normal gravitational environment. The eyes and vision also change in dangerous ways. Scientists discovered in the past few decades that many astronauts return with blurry vision that sometimes does not completely return to normal. The fluid shift toward the head increases pressure inside the skull. This pressure pushes gently against the back of the eye, flattening it and causing the optic nerve to swell. Over long missions, this swelling can lead to permanent changes in vision. Researchers call this condition spaceflight-associated neuroocular syndrome. It proves that the human eye and the brain are deeply affected by microgravity in ways that were not known before humans spent long periods in orbit. The immune system also weakens in space. On Earth, the immune system is always fighting tiny threats, keeping the body safe. But in microgravity, immune cells do not function as well. They respond slowly, become less active, and sometimes fail to multiply when they are needed. Viruses that were dormant inside the body, such as those that cause cold sores or chickenpox, can become active again. Cuts and wounds take longer to heal. The body becomes more vulnerable to infection. Scientists have found that even bacteria behave differently in microgravity, sometimes becoming stronger or more resistant to antibiotics. This raises serious concerns about how illness would spread inside a spacecraft where people live in tight quarters with little access to medical help. Another major threat to human physiology in space is cosmic radiation. On Earth, the magnetic field and thick atmosphere block most harmful radiation from space. But once a person leaves Earth's protection, their body is exposed to high-energy particles from the Sun and from distant stars. These particles can pass through skin, muscle, bone, and even through solid metal walls. Some of this radiation comes in the form of solar wind, which becomes extremely dangerous during powerful solar storms. Even more dangerous are galactic cosmic rays, which come from exploding stars far beyond our solar system. These rays are made of heavy particles travelling at nearly the speed of light, and when they strike the cells inside the body, they damage DNA. Over time, this damage increases the risk of cancer, heart disease, and neurological problems. Cosmic radiation also affects the brain. High-energy particles can pass through the skull and disrupt the electrical signals that brain cells use to communicate. Experiments with animals show that prolonged exposure to space radiation can impair memory, reduce attention, and slow down problem-solving skills. This means that astronauts travelling to distant planets for many months or years could experience declines in mental sharpness. In a spacecraft where every decision matters, even small changes in cognitive function can be life-threatening. Radiation also affects other parts of the body. It can weaken the walls of blood vessels, increasing the risk of cardiovascular disease. It can damage bone marrow, which creates blood cells, lowering the number of healthy cells circulating through the body. It can harm reproductive cells, which raises concerns about whether humans can safely conceive or raise children in space. Radiation can also accelerate aging because it damages the structures that keep cells healthy. Some scientists believe that long-term space travel may shorten a person's lifespan because radiation affects nearly every biological system. Physical isolation is another major challenge that affects both the body and the brain. Humans evolved to live in groups, interact with others, and experience sunlight, fresh air, natural sounds, and open space. In a spacecraft, all of these are limited. The environment is small, enclosed, and often stressful. Astronauts on long missions are separated from family, friends, and all familiar surroundings. They wake up each day inside a machine, with the same walls, the same sounds, and the same tasks. This isolation can lead to loneliness, sleep problems, irritability, and emotional strain. The brain is extremely sensitive to isolation. When a person is cut off from normal social and sensory experiences, the brain begins to change. Studies on Earth, done with people in submarines, polar research stations, and isolation chambers, show that long periods of isolation can shrink parts of the brain involved in memory and emotional control. In space, where isolation is stronger and more extreme, the effects may be even greater. Astronauts often struggle with disrupted sleep cycles because they experience many sunrises and sunsets each day. Without natural light and normal day-night rhythms, the body's internal clock becomes confused. This leads to fatigue, mood swings, and difficulty concentrating. Inside a spacecraft, every sound is artificial. The constant hum of machines, the lack of nature, and the absence of quiet can create psychological stress. There is no fresh air, no wind, no smell of plants or soil. The senses are deprived of variety. Some astronauts report feeling disconnected from reality, as though they are living inside a simulation rather than the real world. Others describe emotional numbness, sadness, or anxiety. Even highly trained astronauts sometimes struggle with the mental strain of long missions. The combination of microgravity, radiation, and isolation places enormous pressure on the human body. These factors do not act separately. They interact with each other, creating even more complex health challenges. For example, microgravity weakens the bones and muscles, but radiation also damages bone cells, making bone loss even worse. Isolation affects sleep, and poor sleep weakens the immune system, which is already weakened by microgravity. Radiation harms the brain, and isolation also affects the brain, so the combined effect could be much more severe than either one alone. Another challenge is the fact that the human body uses more resources in space. Even though gravity is absent, stress levels are often higher. Astronauts must constantly monitor machines, handle emergencies, and perform tasks where even a small mistake can be dangerous. High stress releases hormones that weaken the immune system, disturb digestion, and affect mental health. The body also loses fluids more quickly in microgravity, So dehydration becomes more common. Eating becomes more difficult because taste changes in space, partly due to fluid shifts in the head, which affect the way the tongue senses flavour. Some astronauts report that food tastes bland or metallic. Sleep becomes fragmented. The body's natural cycle of sleeping at night and staying awake during the day becomes difficult to maintain because a spacecraft in low Earth orbit experiences one sunrise every 90 minutes. The body relies on sunlight to regulate hormones like melatonin, which controls sleep. Without a stable cycle, astronauts often wake up many times during the night. Poor sleep affects mood, memory, reaction time, and decision-making abilities. On long missions, chronic sleep disruption can lead to more serious mental health challenges. Even the sense of time becomes distorted. Without natural environmental cues, days blend together. The brain struggles to maintain a clear sense of how much time has passed. This makes long missions feel even longer and adds to emotional fatigue. The microbiome inside the human gut also changes in space. The microbiome consists of trillions of bacteria that help digest food, support the immune system, and influence mental health. In microgravity, the balance of these bacteria shifts. Some types grow faster, others die off. This can affect digestion, nutrient absorption, and the chemicals the gut produces that influence mood. Changes in the microbiome can also increase inflammation in the body, which adds more stress to the immune system. The human heart also weakens in microgravity. Because it does not need to pump blood against gravity, it becomes smaller and less efficient. Over time, the chambers of the heart may shrink, the walls may thin. When astronauts return to Earth, their hearts sometimes struggle to adjust. Some experience irregular heart rhythms or low blood pressure when standing up. These conditions can last for months. Another danger comes from the lack of proper medical care in space. On Earth, hospitals have advanced tools, doctors, and specialists. But on a spacecraft, medical equipment is limited. If a person develops a serious illness, experiences a heart problem, or suffers a severe injury, there is very little that can be done. Even a common condition like appendicitis would become life-threatening, because surgery in microgravity is extremely difficult. Blood floats, fluids drift, infection becomes easier because the immune system is weaker. The idea of treating a broken bone, a collapsed lung, or a major infection in space is far more challenging than people realize. Long-term missions also raise questions about reproduction. The human reproductive system evolved under Earth's gravity and radiation-protected environment. Scientists do not yet know whether humans can safely conceive, carry, or deliver babies in space. Radiation can damage sperm and eggs. Microgravity may affect the development of embryos. If humans ever hope to live permanently on another planet, these questions must be answered, but the answers may not be encouraging. Another problem is that the human body regulates temperature differently in microgravity. Sweat behaves differently. Heat does not rise. Warm air does not circulate naturally. The spacecraft must constantly maintain a stable temperature using machines. If those machines fail, the body can quickly become too hot or too cold. Even small temperature changes affect sleep, comfort, and mental health. The human skin also changes in space. It becomes thinner and more fragile. Small cuts or irritations take longer to heal. The constant rubbing of the skin against equipment, straps, and clothing can cause rashes or infections. The lack of fresh air and constant exposure to recycled air can dry out the skin, making it crack more easily. All these changes show that the human body is built for Earth and Earth alone. The environment of space reveals the limits of human physiology at every level. Muscles and bones weaken. The heart slows. The brain changes. Sleep becomes difficult. The immune system grows weaker. The eyes lose clarity. The body loses its sense of balance. The microbiome shifts. The skin becomes fragile. The temperature regulation system struggles. The stress response becomes overactive. Radiation damages cells deep inside the body. Isolation affects mental health in ways that humans are still trying to fully understand. Despite all of this, scientists and engineers continue to study ways to protect the body during long space missions. They develop better exercise machines to slow muscle and bone loss. They test medicines that might help protect cells from radiation. They design spacecraft with thicker shielding. They plan artificial gravity systems that could spin to create a force similar to gravity. They study light therapy to help astronauts sleep better. They experiment with diets that support the microbiome. They test new psychological support systems to help astronauts cope with isolation. But even with these efforts, the limits of human physiology remain a powerful reminder of how deeply connected humans are to Earth. Every system in the human body depends on conditions that exist naturally on only one place known to science. The body expects gravity. It expects Earth levels of radiation protection. It expects natural cycles of light and darkness. It expects fresh air, open space, and social contact. Take these away, and the body begins to fail slowly but surely. This reality shapes every discussion about sending humans to Mars or beyond. A trip to Mars would take many months one way. A person travelling to Mars and back would spend more than 1 full year, or possibly 2 full years, in space. During that time, the body would be exposed to microgravity, cosmic radiation, and isolation all at once. The combined effects, even with the best technology, could leave astronauts with permanent health problems. Their bones would weaken significantly, their immune systems would be compromised, their vision might decline, their cognitive abilities might decrease, their hearts and blood vessels could sustain damage, their risk of cancer would increase for the rest of their lives, their mental health would be under constant strain. The environment on Mars is also harsh. The gravity is only about 1/3 that of Earth. The atmosphere is thin and cannot shield radiation effectively. The temperatures drop far below freezing. The soil contains toxic chemicals. Even if humans reach Mars, the planet will test their physiology in new and unpredictable ways. The limits of human physiology are not failures. They are the result of billions of years of adaptation to a world that supports life. They reveal how special Earth truly is. They also show that any attempt to live beyond Earth must overcome challenges, not just of engineering, but of biology. Every cell inside the human body tells the same story. It was made for Earth. When it's taken away from Earth, it struggles. The challenge of keeping human beings alive far away from Earth for many years or even many decades is one of the most complex problems in all of science and engineering, because it forces us to recreate every single system that our planet provides naturally and effortlessly. When we talk about air, water, food, and waste management on Earth, we are really talking about an invisible network of natural processes that have been running for billions of years. These processes operate without any need for machines, engineers, or monitoring. But the moment humans step off the surface of our planet and enter deep space or settle on another world, every one of those natural systems must be redesigned from scratch using technology that is still imperfect, fragile, and extremely limited. Life support sounds like a simple phrase, but behind it stand countless scientific challenges. Air must be constantly cleaned, refreshed, and kept in the correct balance so that humans can breathe safely. Water must be recycled again and again with almost no loss, because carrying enough water from Earth to last for many years would require impossible amounts of mass and fuel. Food must be grown, stored, or produced in a closed environment where light, nutrients, soil substitutes, and temperatures must be controlled with extreme accuracy. Waste must be removed, broken down, reused, or repurposed so that it does not build up into dangerous levels of toxins. And all of this must be done using machines that cannot fail for decades at a time. The difficulty becomes even greater when we look at how small errors in a closed life support environment can become life-threatening. On Earth, if a power plant breaks or a water treatment facility shuts down, there are alternatives, backups, resources, and outside environments that can compensate temporarily. In deep space or on a distant planet, there is nothing around you that can help. There is no breeze to blow in fresh oxygen, no river to collect clean water from, no farmland to harvest food in. Everything must come from your own life support system, and the system cannot ever take a break. Scientists often say that a spacecraft or space habitat must function like a miniature Earth. This is because Earth acts as the perfect closed-loop system. The water cycle constantly moves water from oceans to the air, then to rain, and back to the oceans again. The carbon cycle uses plants to pull carbon dioxide out of the atmosphere and release oxygen. Soil bacteria break down waste and convert it into nutrients. These cycles took billions of years to form and are supported by the massive scale of the planet itself. Recreating these processes inside a small spacecraft, a space station, or a habitat on Mars is extremely hard. Understanding the complexity of the challenge requires looking at each major part of life support. Air is the first problem because it is the most immediate. The air we breathe on Earth contains roughly 21% oxygen, about 78% nitrogen, and tiny amounts of other gases. It is constantly refreshed by plants, oceans, and geological processes. When humans breathe, they inhale oxygen and exhale carbon dioxide. If carbon dioxide levels rise just a little too high, it can cause headaches, dizziness, confusion, and eventually unconsciousness and death. Even small shifts in oxygen levels can lead to fires or suffocation. In a closed environment like a spacecraft or a sealed base on another planet, these shifts can happen quickly. To handle this, engineers create systems that scrub carbon dioxide out of the air. These systems use chemicals or mechanisms to capture carbon dioxide and store it or convert it into something less dangerous. But the chemicals inside these scrubbers wear out over time, and the machines can break. On a mission lasting many years or many decades, the crew would need a way to replace these chemicals or restore the system without support from Earth. This is already a major problem because even the International Space Station, which orbits only a few hundred kilometers above Earth, requires supplies and spare parts delivered regularly to keep the air systems running. For longer missions or settlements where resupply is impossible or extremely delayed, this challenge becomes even more serious. Beyond removing carbon dioxide, life support systems must also add oxygen back into the air. On Earth, plants and algae release oxygen naturally. In space, oxygen is usually produced by splitting water molecules into hydrogen and oxygen using electricity, a process known as electrolysis. This process is efficient, but the machines that perform it must work continuously. They must not leak, they must not overheat, and they must not clog from mineral buildup. The hydrogen produced must be safely stored or vented because hydrogen can easily ignite. Over many years, even tiny problems with these machines can accumulate into major risks. Water is another enormous challenge. A human adult needs several liters of water every day just to drink, and many more liters for hygiene and food preparation. Over a mission lasting 10 or 20 years, this can amount to tens of thousands of liters per person. Launching this much water from Earth is physically impossible because water is extremely heavy, and rockets have strict limits on what they can carry. For this reason, all long-term missions must rely on water recycling systems that capture almost every drop of water that the crew uses. These systems must recycle water from sweat, breath, urine, and even the humidity in the air. They must filter out bacteria, salts, toxins, chemicals, and waste particles. They must produce water pure enough to drink safely without causing illness. The recycling machines on the International Space Station can recover around 90% of wastewater, but even this system struggles with maintenance issues and requires frequent replacement parts. Extending such a system to work reliably for 20 or 30 years without help from Earth is a huge scientific challenge. In addition, water storage becomes tricky in space. On Earth, gravity pulls water to the bottom of containers, but in microgravity, water forms floating blobs that stick to surfaces, drift through air, and coat equipment. This means that water tanks must be specially designed, sealed, and pressurized to keep water in the right place. Over long periods, tanks can leak or degrade, water pipes can clog with minerals, filters can stop working. Each of these problems could threaten the survival of the crew. Food adds another layer of difficulty. Humans need a balanced diet with carbohydrates, proteins, fats, vitamins, and minerals. For short missions, astronauts can bring packaged meals from Earth, but even these meals must be stored carefully. Food spoils over time, vitamins degrade, and packaging must be strong enough to withstand radiation and temperature changes. For missions that last for many years, packaged food alone will not be enough. Growing fresh food becomes essential. Growing food in space or on another planet is extremely complicated. Plants need light, water, nutrients, and the right temperature. But they also need an atmosphere with carbon dioxide and oxygen in the proper balance. On Earth, plants rely on soil full of microbes that help break down nutrients. In a spacecraft or Martian base, soil must be replaced with artificial materials like hydroponic or aeroponic systems. These systems require pumps, pipes, nutrient solutions, and careful monitoring. A single blocked pipe or a small fungal infection can wipe out an entire crop. For long-term missions, crops must grow reliably year after year, generation after generation, which is far harder than it sounds. Another issue is the amount of space needed to grow enough food. Plants require surface area and light. On Earth, farms stretch for kilometers, and sunlight is free. In space, artificial light must replace sunlight. These lights require power, and power must come from solar panels or reactors. Solar panels may produce less energy far from the sun or on planets with dust storms. Reactors must be built to last for decades. Every calorie eaten by humans must be replaced by calories grown, and producing these calories requires huge amounts of energy. Waste is the final major component of life support. Waste includes solid waste from food, packaging, and other materials, as well as human waste and biological waste from plants. If waste builds up, it becomes a source of bacteria, mold, and harmful gases. It can attract insects if any escape the habitat. It can poison the environment inside the spacecraft. On Earth, waste is handled using enormous systems: sewage treatment plants, recycling facilities, landfills, compost sites, and natural decomposition. Recreating these processes in a small enclosed space is extremely difficult. Some waste can be recycled directly. Human waste contains nutrients that can be used to grow plants if processed safely. But processing it safely requires heat, chemicals, filters, and machines that must run perfectly. Any contamination can spread dangerous microbes. Solid waste must be broken down or reused. Plastics might be melted and reshaped, metals recycled, or organic waste composted. But each method requires machines that must last many years. If a critical machine breaks, waste could pile up until it becomes hazardous. Putting all these challenges together reveals why life support systems are among the hardest technologies to design for long-term space travel. The systems must work perfectly for time periods longer than anything humans have ever attempted. The longest continuous human presence in space has been on the International Space Station, where astronauts have lived since the year 2000. But even that environment depends heavily on resupply flights from Earth. Spare parts, food, water, and equipment are brought regularly. Without these deliveries, the station could not maintain its life support systems for more than a few months. When thinking about missions to Mars or deep space voyages that could last 20 or 30 years, the life support systems must be far more reliable and much more self-sufficient than anything we currently have. They must operate without constant maintenance. They must detect problems automatically. They must use materials that do not degrade in radiation. They must recycle almost 100% of resources. A deeper scientific problem is that all biological systems depend on a certain level of randomness and complexity. On Earth, ecosystems balance themselves with countless species of bacteria, fungi, insects, plants, and animals. These species interact in ways we do not fully understand. When we try to recreate a closed ecosystem in a laboratory, it often becomes unstable. Sometimes one species grows too fast and takes over. Sometimes nutrients disappear. Sometimes mold spreads and kills plants. In the 1990s, a major experiment called Biosphere 2 attempted to create a sealed environment in which humans could live for long periods. The experiment showed how hard this challenge is. Oxygen levels dropped slowly over time, carbon dioxide levels rose, soil microbes consumed oxygen faster than plants could replace it. The environment became unstable even though it was huge compared to a spacecraft. Another difficulty comes from the psychological effects of long-term isolation. Life support systems require constant monitoring. If something goes wrong, the crew must fix it immediately. This means that people must be able to repair delicate machinery while under stress, possibly while tired, anxious, or sick. If the crew becomes mentally exhausted or overwhelmed, they might miss early signs of a failure. A small mistake could have fatal consequences because the entire environment is artificial. Temperature control is also tied to life support. Humans can only survive within a narrow temperature range. Air conditioners, heaters, fans, and insulators must work constantly. Machines that produce heat must be cooled. Machines that need warmth must be insulated. In space or on another planet, the environment outside may be far hotter or colder than anything on Earth. Mars, for example, can drop to temperatures colder than -100 degrees Celsius during the night. If heating systems fail, water can freeze, pipes can burst, and the air inside a habitat can become dangerous. On the other hand, inside a spacecraft, electronic equipment generates heat. If cooling fails, the temperature can rise to deadly levels. Another layer of complexity comes from the effects of radiation. Radiation in space can degrade plastics, break down electronic circuits, and damage sensors. Over years or decades, even tiny amounts of radiation damage can cause machines to malfunction. Any life support system must be built using materials that can survive radiation for long periods. Energy production is tightly linked with life support. Everything – air purification, water recycling, food production, waste management – requires power. If the power supply drops even for a short period, oxygen levels may fall, carbon dioxide levels may rise, water treatment may stop, and plants may die. On Earth, we rely on huge power grids with countless backup systems. In space, energy is limited. Solar panels have lower efficiency as they age. Dust can cover them. Light from the sun becomes weaker as you travel farther from it. Nuclear reactors can provide power but come with their own risks, including radiation shielding, heat disposal, and fuel supply. Another scientific issue involves gravity. Microgravity affects human health, but it also affects how fluids move, how plants grow, and how machines operate. Pumps behave differently without gravity. Air flows in unusual ways. Bubbles do not rise to the surface. Roots of plants may grow in strange directions. All of these differences create new problems for life support systems. When astronauts breathe, the carbon dioxide they exhale does not naturally drift away from their faces as it does on Earth. Instead, it can form an invisible cloud around them, unless fans constantly move the air. This means air circulation system must operate at all times. A single broken fan in a small room can actually lead to pockets of carbon dioxide forming, which could harm the crew. Over decades, fans must be replaced or repaired many times. Everything in life support is connected. If food production slows, waste decreases, air cycles change, and water usage shifts. If water recycling becomes less efficient, less water reaches crops. If crops produce less oxygen, air quality suffers. These connections mean that a small malfunction in one part of the system can spread quickly to every other part. Engineers call this coupling, and it is one of the hardest things to manage in long-term closed environments. Even storing food long-term is a major scientific problem. Foods contain oils and vitamins that break down slowly over time. Space radiation accelerates this breakdown. Packaged food can lose nutritional value after a few years, even if it still looks safe to eat. Vitamin C, for example, degrades significantly under radiation. A long mission lasting 10 or 20 years would require food that stays nutritious for much longer than anything currently available. Scientists are trying to develop special packaging, radiation-resistant nutrients, and long-lasting rations, but the results are still limited. Another problem is biodiversity. On Earth, people do not eat the same food every day for years. Human biology needs variety. Without variety, nutrient shortages develop. In deep space, variety becomes hard to maintain. Growing many kinds of crops requires space, water, energy, and complicated care routines. Seeds must be stored without degrading. Insects for pollination may need to be included, and managing insect populations in a closed habitat is extremely difficult. Furthermore, all life support systems must be tested under real conditions before being used for actual missions. But testing systems intended to run for 50 years or more is extremely slow. No test can perfectly simulate the real conditions of deep space. Unexpected issues might only appear after many years have passed. Engineers call this long-term failure mode discovery, and it is a major risk. The connection between humans and their life support system is so strong that some scientists argue humans should modify themselves biologically to reduce dependence on oxygen, water, or certain nutrients. But such genetic modification is far beyond current capabilities and raises ethical questions. Because of all these challenges, some researchers propose relying heavily on artificial intelligence to manage the complex web of life support systems. Artificial intelligence could monitor thousands of sensors at once, detect early signs of failure, and schedule maintenance before problems become dangerous. But even artificial intelligence needs power, functioning circuits, and protection from radiation. If the artificial intelligence fails, the crew might struggle to handle the system manually. What makes long-term life support even harder is that systems must be extremely efficient. On Earth, people use resources in large amounts because the planet constantly replenishes them. In space, every drop of water matters, every gram of oxygen matters, every calorie of food matters. Waste must be turned into something useful again. This is known as closed-loop life support. Humans currently do not have a complete closed-loop system that works for many decades. The closest attempts are experimental and incomplete. As missions grow longer, new problems appear. Materials inside the habitat may slowly release harmful chemicals. Plastic surfaces can break down, paint can flake, mold can grow in hidden corners, dust can build up inside machines. Natural microbes living on human skin can spread onto surfaces. Over decades, these changes can affect the entire environment. Humidity levels must also be controlled. Too much humidity causes mold and corrosion. Too little humidity dries out skin and respiratory passages, increasing infection risk. Balancing humidity requires constant monitoring and precise control systems. Another hidden challenge is noise. Life support machines, fans, pumps, filters, air movers create continuous background noise. Over years, this noise can affect sleep, stress levels, and mental health. Engineers must design systems that are both reliable and quiet, which is extremely difficult. The size of the habitat also matters. A larger environment is more stable but harder to launch. A small environment is easier to build but more fragile. In small habitats, small changes have big effects. A single plant dying can alter oxygen balance. A small leak can rapidly reduce air pressure. Engineers call this the scaling problem. Long-term missions will also have to deal with unexpected events. Earthquakes on another planet, dust storms, impacts from micrometeorites, or equipment failures could all add pressure to life support systems. Every emergency increases resource use, requiring the system to operate even more efficiently afterward. Over decades, these emergencies could accumulate into major risks. Because life support is so complex, scientists sometimes create computer models of closed environments. These models simulate airflow, plant growth, chemical reactions, and human metabolism. But models are imperfect. They cannot predict how real biological and mechanical systems will behave over decades. Human behavior is even harder to model. Stress, illness, conflict, or changes in diet can alter the environment. Even cleaning is a challenge. On Earth, dust falls onto surfaces. In microgravity, dust floats in the air and can enter machines. Special filters must trap it. These filters eventually become clogged and must be replaced. Replacement parts must either be manufactured inside the habitat or brought from Earth, neither of which is easy on long missions. As humans move toward long-term missions beyond Earth, life support becomes one of the biggest scientific and engineering challenges to overcome. It requires knowledge from biology, chemistry, physics, environmental science, engineering, computer science, and medicine. It requires systems that can operate continuously for decades without failure. It requires closed cycles that recycle almost all resources. It requires advanced sensors, self-repairing machines, radiation-resistant materials, and genetically adaptable crops. The difficulty arises from the fact that human beings evolved entirely within Earth's environment. Everything about our biology depends on the conditions Earth provides. Replicating these conditions artificially is incredibly hard, because Earth is vast, complex, and perfectly balanced through natural cycles. Even small changes in those cycles on Earth can cause large environmental problems. In a sealed spacecraft or small habitat, even the smallest imbalance can quickly become life-threatening. For these reasons, maintaining air, water, food, and waste systems for many years or decades outside Earth remains one of the greatest challenges humanity has ever faced. And until these scientific obstacles are solved with extremely reliable long-term solutions, long-duration space travel and permanent settlements will remain some of the most difficult goals humanity has ever attempted. The radiation barrier is one of the most serious obstacles standing between humanity and long-term life beyond Earth. When people talk about exploring deep space, building cities on the moon, or sending humans to distant planets, the discussion often focuses on rockets, fuel, habitats, food, and engineering problems that we can see and touch. But far above all of these challenges lies something far more invisible and far more dangerous: the constant storm of high-energy radiation that fills nearly every corner of the universe. Unlike many problems in space travel, radiation is not something that can be turned off, avoided by clever navigation, or solved with one new invention. It is a fundamental part of the cosmic environment, created by processes happening across billions upon billions of kilometers. This radiation does not behave like the gentle rays of sunlight we feel on our skin on Earth. Instead, it arrives as tiny particles moving at almost the speed of light, particles so energetic that they can tear apart the molecules inside human cells. On Earth, people live inside a shield without even realizing it. Our planet is wrapped in a thick atmosphere and protected by a magnetic field generated by the movement of molten metal deep beneath our feet. This magnetic field stretches far into space, forming what scientists call the magnetosphere. Every second it deflects huge amounts of charged particles streaming from the Sun and from the rest of the galaxy. Without this natural protective shell, life on Earth would have faced radiation levels thousands of times higher than what reaches the ground today. This means that every living creature on our planet exists inside a protective bubble that is extremely rare. The moment a spacecraft leaves low Earth orbit and moves beyond this magnetic shield, the crew begins to face an environment that human biology has never had to endure for long periods. The universe contains two main radiation threats that travelers must confront. The first is cosmic rays, which are tiny particles, mainly protons and heavier atomic nuclei, shot out of exploding stars, supernova remnants, black hole jets, and other violent cosmic events. These particles travel at speeds incredibly close to the speed of light. Some cosmic rays have energies thousands of times greater than what particle accelerators on Earth can produce. When these particles strike human tissue, they can slice through DNA, disrupt cell structures, and create chemical reactions that the body struggles to repair. Because they are so energetic, they can pass through several centimeters of metal, plastic, or other materials used in spacecraft construction. Some cosmic rays are so powerful that even several meters of solid rock would not fully stop them. The second threat comes from the Sun. The Sun constantly emits a stream of charged particles called the solar wind, but this is only the beginning. At irregular intervals, sometimes several times a month and sometimes with long quiet periods, the Sun releases sudden bursts of energy called solar flares. Even more dangerous are coronal mass ejections, giant clouds of charged particles hurled into space. When these storms reach Earth, they can disrupt power grids, damage satellites, and create beautiful auroras. But for astronauts outside Earth's magnetic shield, a major solar storm is nothing short of life-threatening. A single powerful solar event can deliver a dose of radiation that would be lethal within hours if a spacecraft or habitat is not equipped with extremely effective shielding. The problem is that current shielding technologies are nowhere near strong enough to guarantee safety from these radiation sources during long missions. Traditional spacecraft walls, made from aluminum or composite materials, can block some radiation, but not nearly enough. When high-energy particles strike metal shielding, they do not simply stop. Instead, they can collide with the atoms in the shield and create secondary particles, fragments of atomic nuclei that continue to travel through the spacecraft. This means that adding more metal can sometimes make the radiation problem worse, not better. Scientists call this nuclear fragmentation, and it is one of the most difficult problems in space radiation protection. To fully understand why radiation in space is so dangerous, it helps to look at what actually happens when radiation enters the human body. Human DNA is made of long chains of molecules arranged in a very precise order. This arrangement acts as an instruction manual for everything the body does, from repairing tissues to producing enzymes. Radiation can break these chains or cause chemical changes that alter their instructions. The body has remarkable repair mechanisms that can fix some of this damage, but they are not perfect. When too many breaks occur, or when damage happens repeatedly over long periods, cells can start malfunctioning. Some begin dividing uncontrollably, which can lead to cancer. Others die or stop performing their proper roles. In the brain, radiation can cause the gradual loss of neurons, leading to memory problems, reduced cognitive ability, or mood disorders. In blood-forming tissues, radiation can impair the immune system. Over long missions, these effects add up. One of the most troubling aspects of cosmic radiation is that it never stops. Even small doses accumulate over time, like tiny cracks forming in a stone. A mission to Mars, for example, would require astronauts to spend several months traveling each way and possibly several months on the surface waiting for the alignment needed to return to Earth. In that entire time, they would remain outside Earth's magnetic shield. Experiments with sensors on spacecraft have shown that astronauts could receive radiation doses several times the maximum levels considered safe for a career astronaut on Earth. Over the length of such a mission, they could accumulate enough exposure to greatly increase their risk of cancer, cataracts, heart problems, and neurological damage. Cosmic rays pose a particularly complicated challenge because they come in many types and energies. Low-energy particles can be blocked with relatively thin shielding materials. Medium-energy particles require thicker layers, but the solutions are still manageable. The real problem is the small fraction of extremely high-energy cosmic rays, those with energies millions or billions of times greater than the rest. These particles behave almost like bullets made of atomic nuclei. They punch through spacecraft walls, through the body, and out the other side in a fraction of a millisecond. They leave behind dense trails of damage inside cells. Even though these ultra-energetic particles are rare, they strike often enough over long missions to pose a serious danger. No technology currently known can fully block them without using impractically thick layers of material. Scientists have explored a long list of possible shielding materials. Metals like aluminum were used for decades because they are strong and easy to shape. But aluminum produces a lot of dangerous secondary radiation when hit by cosmic rays. Plastics containing large amounts of hydrogen atoms work better because hydrogen does not create as much fragmentation. Materials like polyethylene, water, and certain chemical compounds are therefore being considered. Some spacecraft concepts propose surrounding crew cabins with water tanks or fuel tanks to help block radiation. However, this introduces weight problems. Every kilogram added to a spacecraft requires more fuel, which makes missions more expensive and technically difficult. A layer of shielding thick enough to significantly reduce cosmic radiation might require many tens of thousands of kilograms of material, far beyond what rockets can carry into space at the moment. Even if future rockets become more powerful, shielding an entire spacecraft might still be too heavy to be practical. There is also the complication that radiation levels in space are not constant. They change depending on where the spacecraft travels. Near Earth, the magnetic field offers partial protection. This is why astronauts aboard the International Space Station experience higher radiation levels than on Earth, but far lower than what they would face in deep space. Once a spacecraft travels beyond the Van Allen radiation belts, the protective influence drops sharply. For missions to the Moon, this is already a concern, though the travel time to the Moon is relatively short, only a few days. But a mission traveling for many months or years faces far higher cumulative exposure. Solar storms add unpredictability. A solar flare can erupt with almost no warning. In the worst-case scenario, a spacecraft caught in such a storm without adequate shielding would expose its crew to radiation levels so high that symptoms could begin within hours. Nausea, weakened immune function, and dangerous changes in blood chemistry. A strong coronal mass ejection could deliver a dose that far exceeds safety limits even through the shielding currently used on modern spacecraft. To handle solar storms, mission planners consider the idea of storm shelters inside spacecraft. Small, heavily shielded compartments where astronauts can retreat during intense bursts of radiation. These shelters may use water, plastic, food supplies, or other dense materials to create a thick protective barrier. But such shelters only protect astronauts during major solar events, not from the continuous drizzle of cosmic rays, which are the real long-term threat. One scientific challenge lies in how unpredictable cosmic radiation is compared to radiation sources on Earth. On Earth, radiation exposure is carefully measured, predictable, and confined to specific environments like nuclear reactors or medical imaging machines. In space, radiation arrives randomly. One day may bring relatively low rates of particle strikes, while the next brings a surge. There are cycles connected to the Sun's activity, which rises and falls over an approximately 11-year period, but cosmic rays from outside the solar system can actually increase when the Sun is quiet, because the weaker solar magnetic field allows more deep space particles to leak in. The human brain is especially vulnerable to cosmic radiation. Studies using rodents exposed to radiation levels similar to those expected on a mission to Mars have shown worrying effects: reduced ability to remember information, increased anxiety-like behavior, and changes in brain structure. Radiation seems to interfere with the cells that maintain the protective barrier between the blood and the brain. It also creates inflammation within nervous tissue. Over long periods, these changes might reduce an astronaut's ability to make decisions, solve problems, or react quickly, abilities that are crucial in emergencies far from Earth. The possibility that astronauts on long missions could experience cognitive decline raises questions about the safety of missions lasting several years. Another factor is that radiation damages the cardiovascular system. High-energy particles may cause changes in blood vessel walls, promoting the development of atherosclerosis, a buildup of plaque that can lead to heart disease. Even astronauts whose missions lasted only several months on the International Space Station show signs of increased cardiovascular risk later in life. A deep space mission lasting well over a year could magnify these effects. The dangers are not limited to the astronauts themselves. Radiation also affects materials and electronic systems. High-energy particles can change the structure of metals and plastics, making them more brittle over time. They can also disrupt computer chips, cause memory errors, and damage sensors. A spacecraft traveling for several years without extensive protective measures could see its systems slowly degrade, making failures more likely. If a key system fails far from Earth, repairs may not be possible, and rescue would be overwhelmingly difficult. One of the most puzzling facts about cosmic radiation is that we still do not fully understand how dangerous some parts of it are. We have measured radiation levels on spacecraft, but translating those measurements into long-term health predictions remains uncertain. Different types of radiation affect tissues differently. Some cause widely dispersed damage, while others cause dense clusters of DNA breaks in very small volumes of tissue. The body can repair some types of damage more easily than others. This makes it difficult to determine exactly how much shielding is enough. Researchers on Earth use particle accelerators to mimic cosmic radiation, but accelerators cannot reproduce the exact mix of particle types and energies found in deep space. Some cosmic rays, especially heavy atomic nuclei traveling at nearly light speed, are extremely rare and extremely difficult to replicate in a laboratory. This means that astronauts on long missions will face radiation effects that have never been fully studied. Because of all these complications, scientists have started exploring ideas beyond traditional shielding. One idea involves using magnetic fields to deflect charged particles, mimicking Earth's natural magnetosphere on a smaller scale. But creating a magnetic field strong enough to protect a spacecraft would require enormous amounts of energy. Another idea is plasma shielding, where electrically charged gas surrounds the spacecraft and acts as a barrier. These technologies remain experimental and far beyond current engineering capabilities. Even if they become feasible, they may only offer partial protection. Biological solutions are also being considered. Some organisms on Earth, such as certain species of bacteria, fungi, and microscopic animals called tardigrades, have remarkable resistance to radiation. Researchers are studying the molecules and DNA repair mechanisms in these organisms in hopes of discovering ways to strengthen human cells. There have even been proposals to modify human DNA to make people more resistant to radiation, though such ideas raise deep ethical questions and remain theoretical. Another idea is to change mission strategies. Instead of sending humans on one long journey, missions could take advantage of natural protective environments. For example, building habitats inside caves or tunnels on the Moon or Mars would use rock as shielding. Several meters of rock can reduce radiation levels significantly. The challenge is finding or creating such caves, transporting equipment into them, and designing life support systems that operate underground. Even if astronauts live inside protected habitats, they must still travel through unshielded space to reach their destination. Mission planners attempt to reduce exposure by choosing flight paths that minimize time spent in high radiation zones, but travel time cannot be reduced infinitely. Physics sets limits. The faster a spacecraft travels, the more energy it needs. Reaching Mars in only a few weeks, instead of several months, would require propulsion systems far beyond anything currently available. Nuclear propulsion or advanced electric propulsion might shorten trips in the future, but even then, cosmic rays would still pose a threat. The radiation barrier also raises significant concerns for long-term human settlement beyond Earth. Even if small groups of astronauts can endure several months of radiation exposure, larger populations, including children, would face much greater risks. Radiation causes mutations in reproductive cells and increases the chance of birth defects. A colony exposed to high radiation for many generations might accumulate genetic damage. Without strong and reliable shielding, long-term settlement may not be possible. Astronauts today already experience radiation doses hundreds of times higher than people on Earth, despite spending their missions inside the relative safety of low Earth orbit. This demonstrates how powerful the radiation environment becomes when protective layers are removed. The International Space Station benefits from Earth's magnetic protection, but spacecraft traveling to the Moon, Mars, or beyond have no such advantage. One of the most striking pieces of evidence for the severity of space radiation comes from the lunar missions. Astronauts who walked on the Moon during the late 1960s and early 1970s travelled through the Van Allen belts and spent several days outside Earth's magnetic shield. They returned safely because the missions were short and because solar activity happened to be relatively quiet. If a major solar storm had occurred during one of those missions, the astronauts could have received lethal radiation doses before returning home. Their survival was partly a calculation and partly a matter of good fortune. As missions in the future aim to last months or years, relying on luck is unacceptable. Science must find reliable methods of protection. Yet every approach so far runs into a significant challenge. Either it is too heavy, too energy-intensive, too experimental, or too incomplete to fully protect humans. Cosmic rays are not just dangerous because of their energy, they're also incredibly small, far smaller than the wavelength of visible light. This means they slip through materials in ways that differ from how visible light or normal radiation behaves. Their interactions are governed by quantum physics, nuclear physics, and relativistic mechanics. To design shielding, engineers must use complex computer simulations that track particle collisions at atomic scales. These simulations are extremely difficult and computationally expensive. Even when simulations predict success, real-world tests often reveal unexpected fragmentation effects or weaknesses. Cosmic radiation also interacts with spacecraft structure in surprising ways. When cosmic rays hit the aluminum hull of a spacecraft, they can generate showers of secondary particles, including neutrons and gamma rays. These secondary particles can cause more damage than the original cosmic ray. The only way to significantly reduce this is to design shielding materials that minimize fragmentation, typically materials rich in hydrogen. But hydrogen-rich materials tend to be less structurally strong than metals, creating new engineering problems. Some scientists propose using layered shields that combine strong outer materials with hydrogen-rich inner layers. Others explore inflatable shielding modules that expand in space to save launch weight. Some have proposed using the spacecraft's fuel itself as shielding, arranging fuel tanks around the crew cabin. But all of these solutions only reduce radiation, not eliminate it. Even if radiation levels are reduced by half, the remaining exposure on a long mission could still exceed safe limits. Space agencies define certain dose limits for astronauts, but these limits are based on short missions. For multi-year missions, the levels of uncertainty are so high that scientists cannot confidently say what dose is safe. The deeper the exploration, the greater the unknowns. Radiation also accumulates unevenly in the body. Bone marrow, eyes, lungs, skin, and reproductive organs all absorb different amounts. Cataracts are a known long-term effect among astronauts, especially those who flew during the era of the space shuttle. Brain tissue once damaged does not regenerate easily. The combined pressures of isolation, microgravity, and radiation create a complicated picture of long-term health. Microgravity itself may worsen radiation effects. In weightlessness, cells behave differently. Fluids shift, immune function drops, bone density decreases, and oxidative stress increases. These factors may make cells less capable of repairing radiation damage. So the combination of microgravity and cosmic radiation, both unavoidable in deep space, may produce biological outcomes that no one has fully observed yet. Radiation is also one of the main reasons that robotic probes greatly outnumber human missions in deep space exploration. Machines can be built to survive high radiation levels using hardened electronics. Humans cannot. Machines do not develop cancer, neurological decline, or cardiovascular disease. They do not require food, water, or oxygen, and they do not fear solar storms. For now, robots remain our primary explorers beyond the protective shell of Earth, because they can withstand the radiation that humans cannot. Looking toward the future, scientists are exploring the idea of using pharmaceuticals to reduce damage from radiation. Certain compounds can help reduce inflammation, enhance DNA repair, or protect cells from oxidative stress. But medicines can only lessen harm. They cannot stop cosmic rays from entering the body. Medicine may help astronauts cope with radiation exposure, but cannot replace shielding. Another future idea involves using artificial gravity created by rotating spacecraft. Artificial gravity may help the body stay stronger and repair itself more effectively. It does not, however, reduce radiation exposure. Radiation will pass through a rotating spacecraft just as easily as a stationary one. Some researchers suggest using thick layers of lunar or Martian soil to build habitats. Soil, also called regolith, contains a mix of dust, minerals, and small rocks. Several meters of regolith could reduce radiation to levels comparable to those on Earth, but this helps only after astronauts reach the surface. During the months of travel through deep space, they will still face the full radiation environment. The radiation barrier is therefore not a single problem with a single solution. It is a network of interconnected challenges involving physics, biology, engineering, and medicine. It requires understanding particles born in supernova explosions billions of years ago. It requires designing materials capable of slowing particles traveling at nearly the speed of light. It requires building habitats that balance strength, weight, and practicality. It requires analyzing how human cells behave under conditions no human has ever experienced for long periods. Even with new materials, innovative designs, and biological research, the harsh truth remains. The radiation environment beyond Earth is extremely unforgiving. It is one of the clearest signs that space is not designed for life. The cosmos is full of beauty, but also full of invisible forces that have shaped planets, stars, and galaxies for billions of years, forces that living organisms on Earth have been shielded from since the beginning of life. The distance problem is one of the greatest and most unforgiving obstacles standing between humanity and the dream of travelling beyond our home world. Even with all our progress in science, engineering, physics, and space exploration, the vastness of the universe is so overwhelming that it pushes the limits of what our machines can do and what human bodies can endure. When people talk about space, they often imagine planets, stars, galaxies, and distant worlds as if they are arranged on a map and separated by distances we can simply cross with enough fuel or enough motivation. But the reality is very different. The distance between Earth and even the closest places in the universe is so enormous that our fastest spacecraft would need many human lifetimes just to reach them. The more we learn about the size of the cosmos, the clearer it becomes that distance is not just a challenge. It is a barrier so immense that it almost feels like a rule of nature preventing us from leaving our tiny corner of space. To understand this distance problem, it helps to begin with something familiar. Our planet Earth orbits the Sun, and the Sun is part of a solar system that contains planets, moons, asteroids, and other objects. The distance between Earth and the Sun is about 150 million kilometers, which scientists call one astronomical unit. When explained in words, that number may seem big, but compared to the rest of the universe, it is tiny, almost nothing. Light from the Sun, travelling at the fastest speed possible in the universe, takes only about 8 minutes to reach Earth. But if we try to travel the same distance using a spacecraft, even our fastest probes need months. This comparison already hints at the scale of the challenge. Light moves at a speed that nothing in the universe can beat, yet even it takes time to cross the space between Earth and the Sun. Human-built spacecraft, which are many thousands of times slower than light, struggle to cover even small fractions of these cosmic distances, and that is only within our solar system. Once we look beyond the Sun, the scale becomes much more extreme. The nearest star to Earth, apart from the Sun, is Proxima Centauri. It is located more than 4 light-years away. The term light-year means the distance light travels in 1 year. So if light, which is the fastest thing in existence, needs more than 4 years to get to the nearest star, we can begin to imagine how long it might take a spacecraft moving at a much slower speed. A light-year sounds like a unit of time, but it is actually a measure of distance. If we convert 1 light-year into kilometers, the result is a number with so many zeros that it becomes almost impossible to visualize. When scientists say that something is several light-years away, they are describing distances that are truly massive, so large that nothing in human experience even comes close. Human beings have built spacecraft capable of reaching very high speeds by the standards of technology, but even the fastest ones are unbelievably slow when compared to the scale of interstellar space. One example is the Voyager 1 probe, launched by NASA in the year 1977. It has been travelling through space for more than 4 decades, moving at a speed of roughly 17 kilometers per second. That is extremely fast for a machine made by humans. At that speed, you could circle the Earth in a few minutes. But even travelling that fast, Voyager 1 would still need tens of thousands of years to reach the nearest star. In other words, the fastest spacecraft we have ever created cannot get us outside our solar neighbourhood within any reasonable human time frame. Even if a person boarded such a vessel at birth, They would never live long enough to see it reach even the edge of the Oort cloud, the boundary of icy objects surrounding our solar system, which itself is still only a tiny part of the full universe. This enormous scale introduces a fundamental problem. Human life is short compared to cosmic distances. A typical human being lives for under a century. Even if technology improves and life expectancy increases, it remains impossible for someone to survive for thousands or millions of years without extraordinary biological or technological changes. If our spacecraft require tens of thousands of years to travel between stars, then a single human-performed mission becomes pointless. Entire civilizations could rise and fall on Earth before a spacecraft traveling at current speeds could complete an interstellar journey. This makes it clear that the biggest problem with distance is not simply the space itself, but the time required to cross it. The universe is spread out over such vast regions that the human lifespan becomes insignificant compared to the time required for travel. Another important factor is energy. To travel across space faster, a spacecraft needs incredible amounts of energy. The faster you want to go, the more energy you must use. But accelerating to even a fraction of the speed of light requires energy levels far beyond anything humanity can produce today. The laws of physics tell us that the closer you get to the speed of light, the more your mass effectively increases, and the harder it becomes to accelerate any further. This is part of Albert Einstein's theory of relativity. According to this theory, reaching the speed of light is impossible for any object with mass, because it would require infinite energy. This rule applies to everything humans could ever build. So even if we try our best, we will always be limited to speeds far below that of light. There have been ideas about using nuclear energy, antimatter, or even hypothetical propulsion systems like warp drives or wormholes. These concepts appear in scientific papers and science fiction stories, but so far none of them are close to becoming real. Antimatter, for example, contains enormous amounts of energy, and a single gram of antimatter could theoretically produce more energy than a nuclear bomb. But creating antimatter requires energy equal to or greater than what it outputs, and storing it safely is almost impossible because it destroys any normal matter it touches. Warp drives and wormholes, while interesting, require physics that we do not yet understand and materials that may not even exist. These ideas show how desperate scientists are to overcome the barrier of distance, but they also highlight how difficult the challenge truly is. Even travelling within our own solar system is far more difficult than people realise. The planet Mars, which is often discussed as the next target for human exploration, is relatively close to Earth compared to other planets, but even it is tens of millions of kilometres away. A spacecraft travelling to Mars takes about 7 months or more to arrive, depending on the alignment of the planets. And getting to Mars is nothing compared to travelling to the outer planets. Jupiter is hundreds of millions of kilometres away, while Neptune is about 4 billion kilometres from the Sun. When we send probes to these distant planets, the missions take many years to complete. The New Horizons mission, which flew past Pluto in the year 2015, took nearly a decade to reach its target. And Pluto is still inside our own solar system. The moment we try to look beyond that, the distances grow so large that they become almost unthinkable. Another aspect of the distance problem is that space is mostly empty. Even though the universe contains trillions of stars and galaxies, the space between them is enormous. Galaxies themselves are separated by millions of light years. Travelling from one galaxy to another is far beyond anything humans can achieve. Our own Milky Way galaxy is about 100,000 light years across from one side to the other. Even if a spacecraft could travel at 1% of the speed of light, which is far faster than anything humans have created, it would still take thousands of years to move from just one part of the galaxy to another. And 1% of the speed of light is not something we can currently achieve. Reaching even a small fraction of the speed of light requires propulsion systems that do not yet exist. Because space is so big, communication becomes part of the distance problem too. When a spacecraft travels far away from Earth, signals take longer and longer to travel back and forth. Light signals, such as radio waves, still move at the speed of light, but the distance adds delay. For example, when the Voyager spacecraft send messages back to Earth, it takes more than 20 hours for the signal to arrive. If a spacecraft travelled to another star, the delay would be measured in years. This communication delay means that remote missions become extremely difficult to control. By the time Earth receives a message, the situation might have changed completely. Autonomous spacecraft would be necessary, but even then, The delays complicate navigation, problem-solving, and safety. Scientists often describe the universe as a vast desert, with small islands of matter surrounded by enormous empty spaces. Travelling between these islands is like trying to cross an ocean without a map, without fuel stations, and without any hope of help if something goes wrong. Every journey requires carrying everything needed for survival, including fuel, food, water, air, and spare parts. As distances increase, the amount of supplies required becomes too great to transport. Fuel itself becomes a major limitation. The more fuel you carry, the heavier the spacecraft becomes. The heavier it becomes, the more fuel you need just to move that fuel. This creates a cycle that quickly becomes impossible to sustain. This is one reason rockets are built in stages and why they shed empty fuel tanks as they rise. But for interstellar travel, the scale becomes too large for such methods to work. Carrying enough fuel to accelerate, decelerate, and navigate over light-year distances becomes unrealistic. Many futuristic proposals try to solve the fuel problem by using energy from outside the spacecraft, such as solar sails pushed by light or giant lasers on Earth. Solar sails use the pressure of sunlight to move a spacecraft slowly over long periods. The idea is promising, but still requires huge, delicate, lightweight sails that we cannot yet build at the necessary scale. Light also becomes weaker the farther you travel from the sun, so solar sails become less effective in deep space. Laser-powered sails could work, but they require massive ground-based lasers of enormous power and precision, which humanity has not yet constructed. Even if we built them, steering a small sail across billions of kilometers with a laser beam accurately enough to keep it moving in the right direction is incredibly difficult. The challenge of distance also becomes more severe when we consider human needs. Humans need more than just air and water. They need protection from radiation, comfortable living environments, temperatures within survivable limits, healthy food, medical care, tools, psychological support, and a stable gravity-like environment to maintain bone and muscle health. The farther a ship travels, the harder it becomes to provide these essentials. A trip lasting thousands of years would require generations of people to live and die on a spacecraft. This leads to the idea of generation ships, enormous vessels where entire societies live, reproduce, and grow old while the ship continues on its journey. But such ships would require resources comparable to small cities or even nations. They would need closed-loop life support systems capable of working without failure for millennia. Even a single malfunction in food production or waste recycling could destroy the entire mission. No technology on Earth today can operate perfectly for thousands of years without maintenance, repair, or replacement. Another proposed solution is cryogenic sleep or suspended animation, where humans are frozen or put into a state of slow, biological activity to survive long journeys. But we do not have the technology to freeze a human safely and revive them without damage. Even freezing small animals is extremely difficult. Human cells form ice crystals when frozen, which damage tissues. Cryoprotectant chemicals can reduce freezing damage but cannot stop it entirely. Until scientists discover a way to freeze and revive humans safely, this option remains impossible. Some have suggested sending only artificial intelligence or robotic probes instead of humans. Robots do not age, do not require food, and do not suffer from health problems. They could theoretically travel for thousands of years. But even this solution has challenges. Machines degrade over time, electronics are damaged by cosmic radiation, computer systems can fail, robots still need power, and power sources eventually run out. Designing a robotic probe that could survive and function independently for tens of thousands of years is beyond our current engineering capabilities. There is also the psychological aspect. Humans are social creatures who depend heavily on their surroundings. Even astronauts who spend only a few months on the International Space Station sometimes experience strong emotional challenges due to isolation, limited movement, and the lack of natural environments. A journey lasting many decades or generations would put extreme stress on the minds of the people on board. Isolation, confinement, boredom, and the knowledge that they may never see Earth again could lead to mental health problems. Maintaining a stable society inside a spacecraft for thousands of years is incredibly difficult. Even small disagreements could grow into dangerous conflicts when there is no way to escape or seek outside help. Cosmic distances also raise the problem of navigation. In space, there are no roads or landmarks. Spacecraft navigate using the positions of stars, planets, and other celestial objects. But when travelling for thousands of years, even small errors in navigation could cause the ship to drift off course by huge distances. A tiny misalignment of less than a degree could eventually place the ship in a completely different region of space than planned. Correcting such errors would require fuel and precise manoeuvring, which add to the energy problem. Not to mention that celestial objects move over time. Stars orbit the centre of the galaxy, and their positions shift over thousands of years. A target star system may not even be in the same position by the time a spacecraft arrives. When we consider all these challenges together, the distance problem becomes even more daunting. It is not just a matter of having a fast enough spacecraft. It is about overcoming limitations in physics, energy, engineering, biology, psychology, and society. It requires building machines that last longer than civilizations, storing energy more efficiently than any known technology, and protecting life from the hostile environment of space over unbelievable timescales. The scale of the universe is so vast that even travelling to the nearest star feels like climbing a mountain that grows taller with every step. Every time we develop better technology, the universe seems to remind us that its distances are far greater than we imagined. It is like trying to cross an ocean that never ends, where every problem we solve reveals another, more difficult one waiting ahead. This is why many scientists believe that interstellar travel may not be possible for humans with any technology we can imagine today. Even if breakthroughs occur, the distances are so enormous that travel would still take extremely long periods. Some propose that the only way to overcome the distance problem is by using methods that bend or distort space itself, such as hypothetical warp drives that compress space in front of a ship and expand it behind. But these ideas remain theoretical. They involve exotic forms of matter that have never been observed, and even if they were possible, controlling space at such a scale would require unimaginable amounts of energy. Another idea is using wormholes, which are theoretical shortcuts through space-time. A wormhole could, in theory, connect two distant points in space instantly. But wormholes have never been detected, and if they exist, they might be too small, too unstable, or too dangerous to use. Creating or stabilizing one would require negative energy or unusual physical conditions that humans cannot achieve. So while wormholes are fascinating to think about, they remain speculative and far beyond our current reach. For now, the distance problem keeps humanity confined to our solar system. We can explore planets, moons, asteroids, and comets. We can send probes to the edge of the sun's influence, but once we try to go farther, we run into the wall of cosmic distance. Every step beyond becomes exponentially more difficult. Even sending signals to distant stars takes years, and the universe is filled with billions of galaxies, each containing billions of stars. The scale is simply too big for travel based on engines, rockets, or even the most advanced propulsion systems we can imagine. The challenge of moving a spacecraft beyond our solar system is unlike anything humanity has ever attempted. When we think about sending a spacecraft to even the nearest stars, we must confront a single, overpowering obstacle: energy. The universe is unimaginably vast, and distances between stars are so enormous that conventional methods of travel become almost meaningless. Even reaching the closest star beyond our Sun, Proxima Centauri, which lies about 4.22 light-years away, requires thinking in terms that go far beyond what we currently do with rockets and fuel. To understand why this is so, it is essential to appreciate what it means to accelerate a spacecraft to a significant fraction of the speed of light, a velocity that, for the sake of clarity, is roughly 300,000 kilometers per second, or approximately 186,000 miles per second. The concept of speed in interstellar travel is not merely a question of how fast a vehicle can move through space, but rather how energy scales with speed. In classical Newtonian physics, the energy required to accelerate an object is proportional to the square of its velocity. This means that if a spacecraft were to double its speed, it would require 4 times as much energy. However, when we approach a meaningful fraction of the speed of light, the rules of physics as described by Albert Einstein's theory of relativity begin to dominate. In these conditions, the energy requirement does not just increase quadratically, it rises dramatically, approaching infinity as the spacecraft nears the speed of light itself. To put it simply, no matter how advanced our technology becomes, reaching a significant portion of the speed of light is a task that demands more energy than any source we currently possess on Earth can supply. To provide a sense of scale, consider a spacecraft with a modest mass of just 10,000 kilograms, which is roughly the weight of a small bus. If we attempted to accelerate this spacecraft to 10% of the speed of light, using classical Newtonian calculations, the kinetic energy required would be on the order of 4.5 times 10 to the 18 joules. To make that figure more relatable, the entire annual electricity consumption of the United States is approximately 4 times 10 to the 20th joules, meaning that accelerating even a relatively small spacecraft to a fraction of light speed would demand energy equivalent to a significant percentage of the entire yearly energy use of a major industrial nation. When relativistic effects are considered, as they must be for speeds approaching the speed of light, the energy required grows even larger, quickly reaching levels that stretch the imagination. Traditional chemical rockets, the kind used to launch spacecraft into Earth orbit, are almost hopelessly inadequate for this task. The energy stored in chemical bonds such as those in liquid hydrogen and oxygen is far too low to provide the velocity required for interstellar travel. To reach even a few % of the speed of light, the amount of fuel a chemical rocket would need grows exponentially, quickly becoming impractical. For example, if we were to attempt to accelerate a spacecraft to 5% of the speed of light using conventional rocket fuel, the mass of fuel alone could easily exceed the mass of the spacecraft by a factor of hundreds, or even thousands, depending on the efficiency of the propulsion system. This fundamental limitation forces scientists and engineers to consider alternative methods of propulsion, many of which remain theoretical or experimental. One promising concept is nuclear propulsion, which harnesses the energy released from nuclear reactions. Nuclear fission, the splitting of heavy atomic nuclei such as uranium or plutonium, can release millions of times more energy per unit mass than chemical reactions. In theory, a fission-based spacecraft could achieve a velocity approaching 10% of light speed with a fuel-to-mass ratio far more reasonable than chemical rockets. However, even fission has limits. The energy density, while enormous compared to chemical fuel, is still many orders of magnitude lower than what would be required to reach higher fractions of the speed of light, such as 20% or 50%. Furthermore, managing nuclear reactions safely in a spacecraft traveling through the harsh environment of space presents an array of engineering challenges, from shielding the crew against radiation to controlling the reactor under extreme conditions. Fusion propulsion, on the other hand, offers even greater potential. Nuclear fusion, the process that powers stars like our Sun, releases energy by combining light atomic nuclei such as isotopes of hydrogen, namely deuterium and tritium, into heavier elements. The energy yield from fusion is staggering. A single kilogram of fusion fuel could, in theory, release energy equivalent to millions of kilograms of chemical rocket fuel. If perfected, fusion propulsion could accelerate spacecraft to significant fractions of the speed of light in ways that are theoretically achievable, though the practical difficulties remain immense. Containing and sustaining fusion reactions in a controlled manner, especially in the compact environment of a spacecraft, is a technological hurdle that has eluded humanity for decades, despite substantial progress in laboratory settings on Earth. Beyond nuclear-based propulsion, scientists have proposed entirely different approaches, such as antimatter propulsion. Antimatter, the counterpart to ordinary matter, releases energy through annihilation when it comes into contact with regular matter. The energy density of antimatter is extraordinarily high. 1 kilogram of antimatter interacting with 1 kilogram of matter could produce approximately 9 times 10 to the 16 joules of energy, according to Einstein's equation E equals mc squared. This is roughly 1 billion times more energy than is released from burning a kilogram of chemical fuel. In theory, antimatter engines could propel a spacecraft to velocities approaching the speed of light itself, yet antimatter is extremely difficult and expensive to produce, store and manipulate. Current technology allows only minute quantities to be created in particle accelerators at enormous energy cost, making it entirely impractical for large-scale space travel at present. The energy problem becomes even more daunting when considering the need to slow down upon reaching a target star system. Accelerating a spacecraft to a high fraction of the speed of light is only half the challenge. If the spacecraft is intended to enter orbit around an exoplanet or to safely land, it must decelerate by expelling or otherwise dissipating an equivalent amount of energy. This doubling of energy requirements further strains the feasibility of interstellar missions and makes any discussion of energy management a central concern in the planning of such endeavours. Even with exotic propulsion systems, the problem of braking at destination is an enormous engineering hurdle. Concepts such as using magnetic sails to interact with the interstellar medium, or deploying large photon sails to use the pressure of stellar light for deceleration, have been proposed, yet all involve complex trade-offs and careful calculations of energy efficiency. Another aspect of the energy challenge is the sheer scale of fuel storage and spacecraft mass. Traditional chemical rockets operate on the principle that more fuel means more speed, but carrying enormous amounts of fuel increases the spacecraft's mass, which in turn increases the energy needed to accelerate it, creating a vicious cycle. This is known as the tyranny of the rocket equation, named after Konstantin Tsiolkovsky, who first formalized the relationship between velocity, fuel mass, and spacecraft mass. Even with nuclear propulsion, the mass of the required fuel remains a central design constraint. A spacecraft capable of reaching 10% of light speed could still require tens or hundreds of tons of fuel, depending on its size and the efficiency of its engines. Managing this fuel safely, in the form of solid, liquid, or plasma materials, is a monumental technical challenge, especially considering the need to prevent catastrophic failure during acceleration and the long journey through space. Energy is also critical in other aspects of interstellar travel beyond propulsion. Life support systems, communication, and navigation all require continuous energy supply over potentially decades or even centuries. A spacecraft traveling to even the nearest stars at 10% of the speed of light would take more than 40 years to arrive, meaning that every system aboard must function reliably for decades without the possibility of resupply. This places additional pressure on energy efficiency and storage solutions. Solar panels, a common source of energy for spacecraft within our solar system, become nearly useless in the distant reaches of interstellar space, where the intensity of sunlight diminishes dramatically with distance. Nuclear-based power sources such as radioisotope thermoelectric generators or small fission reactors offer alternatives, but again, these technologies introduce mass, complexity, and risk into the spacecraft design. The challenge of energy is further compounded by the interaction of spacecraft with the interstellar medium. Even the near-perfect vacuum of space is not entirely empty. Tiny particles, cosmic dust, and interstellar gas exist in extremely low densities. But at relativistic speeds, collisions with these particles can produce enormous kinetic energy, effectively acting as a constant drag on the spacecraft. Shields and protective systems must be designed to absorb or deflect these impacts, which themselves require additional energy and mass. Furthermore, cosmic radiation and high-energy particles present continuous threats to both human passengers and electronic systems, demanding additional shielding and active protection systems that consume power. From a more theoretical perspective, concepts such as light sails or laser propulsion attempt to bypass some of these energy limitations. In these systems, an external source of energy, such as a powerful laser beam, pushes a lightweight sail attached to the spacecraft, converting energy directly into acceleration without requiring the spacecraft to carry all of its fuel. Projects like Breakthrough Starshot, announced in 2016, envision using such methods to accelerate tiny gram-scale probes to 20% of light speed using arrays of ground-based lasers. While this concept offers a dramatic reduction in onboard energy requirements, it introduces new challenges, including the need for unprecedented laser power, extreme precision in aiming over interstellar distances, and the fragility of miniature spacecraft traveling at such high velocities. Energy requirements also have profound implications for the feasibility of crewed interstellar travel. While unmanned probes can be made extremely lightweight, crewed spacecraft require life support, radiation shielding, food, water, and psychological considerations for humans. Each additional kilogram of mass translates directly into exponentially higher energy needs for propulsion. For a spacecraft capable of carrying even a small crew to another star, the energy required may exceed anything humanity can reasonably generate, store, or manage with foreseeable technology. This is why many researchers argue that crewed interstellar missions may remain beyond reach for centuries, if not millennia, unless revolutionary new energy technologies emerge. The energy problem is further magnified when we consider practical constraints on energy generation. Current energy sources on Earth, including fossil fuels, nuclear power, and renewable sources, operate on scales that are enormous for terrestrial purposes, but tiny compared to the needs of interstellar travel. Even assuming the development of highly efficient energy generation technologies, creating and storing the energy required to propel a multi-ton spacecraft to significant fractions of light speed presents a societal and logistical challenge on a planetary scale. Entire nations might need to dedicate substantial fractions of their resources solely to energy production for a single interstellar mission. The question of energy also intersects with the limits of our current understanding of physics. The speed of light represents a fundamental barrier, and as we approach it, relativistic effects dominate, not just in energy calculations but also in time dilation, mass increase, and the behavior of matter and radiation. These effects mean that energy requirements rise toward infinity as we near light speed, placing an unbreachable theoretical ceiling on propulsion methods within our current physical laws. To overcome these limits, humanity would need either a paradigm shift in our understanding of physics or the discovery of exotic phenomena, such as negative energy densities or warp fields, which remain entirely speculative at this stage. The construction of a spacecraft is one of the most intricate and delicate endeavours that human beings have ever attempted. While we have learned to build vessels that can survive the harsh environment of low Earth orbit for years, or even travel across the solar system to explore distant planets and moons, the challenge of sending a ship beyond the solar system is a completely different order of difficulty. Unlike operating in the comparatively close and somewhat familiar confines of near-Earth space, interstellar travel confronts engineers and scientists with an environment that is fundamentally hostile, unforgiving, and full of threats that we are only beginning to understand. One of the most pressing dangers to such a spacecraft is the fragility of the vessel itself. Even the most advanced spacecraft, crafted from state-of-the-art materials and technologies, remains vulnerable to a multitude of factors, ranging from tiny micrometeoroids to cosmic debris, from slow material degradation to high-speed collisions with particles that can puncture, crack, or erode the ship over time. Understanding these threats in full detail requires us to examine the environment outside our solar system and to understand the nature of space itself. The first and perhaps most immediate threat to any long-term spacecraft is the constant bombardment by micrometeoroids. These are particles that are often no larger than grains of sand, sometimes even smaller, yet they travel at extraordinary velocities. In the vacuum of space, even a particle as small as a millimeter can strike a spacecraft at speeds exceeding tens of kilometers per second. To put this in perspective, a millimeter-sized fragment moving at such speed possesses the kinetic energy of a small bullet fired from a high-powered rifle on Earth. Over the course of months or years, countless micrometeoroids can impact the surface of a spacecraft. While a single particle may seem negligible, the cumulative effect of thousands or millions of impacts can slowly compromise the integrity of a spacecraft's hull. Tiny punctures, microscopic cracks, and superficial abrasions can gradually grow into weaknesses that threaten the vessel's structural stability. In addition to micrometeoroids, space is filled with human-made debris. Since the launch of Sputnik 1 in the year 1957, humanity has been placing objects in orbit around Earth. Rockets, satellites, old instruments, and fragments from collisions have accumulated in various orbital bands, creating a dense cloud of debris in the near-Earth environment. While most of this debris remains confined within the solar system and the orbits around the planets, spacecraft leaving the solar system will pass through regions where remnants of planetary formation, lost asteroids, and particles ejected from collisions in the asteroid belt or Kuiper belt may exist. These particles may be far less numerous than the debris around Earth, but they travel at speeds that can easily exceed hundreds of kilometers per second, particularly when affected by gravitational interactions with planets and stars. At such velocities, even a particle smaller than a pinhead can create a hole, damage sensitive instruments, or, in a worst-case scenario, breach a pressurized compartment, endangering the lives of any onboard crew or the integrity of the mission. A major problem is that collisions with micrometeoroids and debris are fundamentally unavoidable. Unlike weather systems on Earth, which can be predicted and tracked, these particles are scattered across vast regions of space in a nearly random pattern. While radar and optical instruments allow us to track larger objects in near-Earth orbit, particles smaller than a few centimeters are invisible to most sensors. This means that a spacecraft traveling beyond the solar system, which may take decades or even centuries to reach its destination, cannot avoid these tiny but potentially lethal projectiles. Engineers therefore attempt to design protective measures, such as Whipple shields, which are layers of material separated by gaps that absorb and dissipate the energy of incoming particles. While effective against small fragments, these shields add weight and complexity to the vessel, and they may not be sufficient against larger or faster particles encountered over decades of interstellar travel. The fragility of a spacecraft is further challenged by material degradation over time. Even in the absence of direct collisions, the constant exposure to the vacuum of space, extreme temperatures and radiation can slowly erode structural materials. Metals, composites, and polymers all behave differently in the harsh environment of space. Metals may experience fatigue from repeated thermal cycling, as temperatures swing from hundreds of degrees below zero in the shadow of a planet or interstellar cloud to hundreds of degrees above zero in direct sunlight. This repeated expansion and contraction can create tiny cracks, eventually weakening beams, panels, and support structures. Polymers, such as plastics used in insulation, seals, and electronics, can become brittle over time, cracking or breaking under mechanical stress. Even ceramics and glass, which are often chosen for their resistance to heat and radiation, can suffer from microfractures induced by thermal shock or energetic particle impacts. Radiation plays a particularly insidious role in the degradation of spacecraft. Beyond the protective envelope of Earth's magnetic field, and even beyond the influence of the Sun's heliosphere, cosmic rays bombard any vessel that ventures into interstellar space. These are highly energetic particles, often protons or atomic nuclei stripped of electrons, moving at speeds approaching the speed of light. When these particles strike a spacecraft, they can damage both electronics and structural materials. Over time, radiation can break chemical bonds, weaken metals, and alter the properties of polymers, making them more prone to cracking and failure. Electronics are especially vulnerable. High-energy particles can flip bits, corrupt memory, and even permanently damage components in ways that are difficult or impossible to repair remotely. This cumulative damage is one of the reasons why long-term interstellar missions must be designed with extreme redundancy, shielding, and radiation-hardened systems, all of which increase mass and complexity, further complicating the mission. Another subtle but important threat comes from erosion, caused by tiny particles in interstellar space. While space is mostly empty, it is not a perfect vacuum. Interstellar space contains sparse clouds of gas and dust, often traveling at significant speeds relative to a spacecraft. Collisions with these particles may seem negligible individually, but over the course of decades or centuries, they can slowly wear away surfaces, polishing or thinning protective coatings, scratching instruments, and degrading optical surfaces such as telescope lenses or sensors. Even extremely hard metals and ceramics are not immune to this slow but relentless abrasion, particularly when traveling at speeds that are a significant fraction of the speed of light. For example, a particle traveling at 1/10 the speed of light carries enormous kinetic energy, far exceeding the energy released by a small explosion, despite its minuscule mass. The fragility of spacecraft is also revealed by the limits of mechanical systems. Gears, motors, valves, bearings, and other moving parts are designed to operate under conditions familiar on Earth, or within the controlled environment of a laboratory. In space, lubricants may evaporate or degrade, seals may dry out or crack, and metals may seize due to thermal extremes or radiation exposure. Even systems designed for long-term operation, such as those used on space probes like Voyager 1 and Voyager 2, eventually show signs of wear. The Voyager probes, launched in 1977, are remarkable examples of long-lived spacecraft still transmitting data more than 45 years later. Yet their power sources are gradually decaying, and many instruments have already ceased operation, in part because the physical materials and mechanical systems can only endure so much wear and tear over time. Extrapolating this to interstellar travel, which might last hundreds or even thousands of years, the fragility of a vessel becomes even more concerning. Temperature extremes too are a relentless adversary. Space is not uniformly cold. A spacecraft can be exposed to intense sunlight or plunged into the darkness of deep space, depending on its orientation and trajectory. In interstellar space, the sun becomes a distant point of light, and the vessel is left to contend with temperatures near absolute zero, roughly minus 273 degrees Celsius. These conditions can cause metals to contract dramatically, electronics to behave unpredictably, and fluids to freeze solid. While insulation, heaters, and carefully designed thermal systems can mitigate these effects. They are not perfect, and the energy required to maintain optimal temperatures over decades or centuries is enormous. Any failure in thermal regulation could compromise structural integrity, damage critical systems, or even destroy the vessel outright. The fragility of spacecraft is further illustrated by the challenges of maintaining pressurization and life support for crewed vessels. In the vacuum of space, even a tiny leak in the hull can be catastrophic. Micrometeoroids, debris, material fatigue, or accidental mechanical damage could puncture a wall, allowing air to escape and threatening the lives of astronauts. Long-duration missions require airtight compartments, multiple redundancies, and continuous monitoring to ensure that any breach is detected and mitigated. Even with these precautions, the risk of cumulative damage over decades or centuries is high, as small vulnerabilities may go unnoticed until they become critical. The problem is compounded when considering propulsion systems. Most interstellar mission concepts require continuous or periodic operation of engines, whether for acceleration, course correction, or deceleration. These systems involve complex machinery, fuel tanks, pumps, and nozzles, all of which are susceptible to wear and damage. Tiny debris particles impacting propellant lines, pumps, or valves could disrupt fuel flow, reduce thrust, or even trigger catastrophic failure. Similarly, electrical propulsion systems such as ion thrusters rely on delicate grids and electromagnetic fields that can be disrupted or eroded by constant particle impacts or radiation-induced degradation. Over time, the fragility of these critical systems becomes a central limiting factor in mission design. Communication systems are also at risk. To maintain contact across interstellar distances, spacecraft must rely on extremely precise antennas and transmitters. Even slight damage to antenna surfaces or degradation of materials due to radiation and particle impacts can reduce signal strength or prevent communication altogether. At distances measured in light years, the ability to send and receive data becomes a vital lifeline, not only for scientific observations but also for the safety of any onboard crew. A fragile communication system could isolate a vessel entirely, leaving it blind and unheard in the vast emptiness of space. Finally, there is the question of repair and maintenance. On Earth, when a machine shows signs of wear or damage, we can repair it relatively quickly. In orbit around Earth, astronauts aboard space stations can perform repairs using spare parts and tools. In interstellar space, however, there is no such support. Any damage must be managed by onboard systems or by robotic maintenance, and only within the limits of what was designed and stored for the journey. Fragility, therefore, is amplified. What might be a minor inconvenience near Earth can become a mission-ending problem in the far reaches of space. The inability to replace or reinforce materials makes every puncture, scratch, or crack a potential existential threat to the mission. In summary, the fragility of spacecraft represents one of the greatest barriers to long-term space travel, especially for missions leaving the solar system. Tiny micrometeoroids, cosmic debris, radiation, material fatigue, temperature extremes, erosion, mechanical wear, and the limitations of life support and propulsion systems all combine to create a hostile environment where even the most advanced vessels are under constant threat. This fragility is not merely a matter of engineering inconvenience. It is a fundamental limitation that constrains mission duration, design, and feasibility. To ensure survival over decades, centuries, or longer, future spacecraft must be built with materials that resist damage, systems that are highly redundant, shielding that can protect against high-energy particles, and maintenance capabilities that can operate autonomously in the absence of human support. Despite decades of advances in materials science, robotics, and space engineering, the fragility of spacecraft remains one of the starkest reminders that leaving the protective environment of the solar system is not simply a matter of speed or propulsion. It is a battle against the relentless, unforgiving forces of the cosmos itself. The story of spacecraft fragility is illustrated by existing examples. The Hubble Space Telescope, launched in 1990, has faced continual challenges from micrometeoroid impacts, thermal stress, and the slow degradation of materials. Even in low Earth orbit, engineers have had to perform multiple servicing missions over decades to repair and replace components. The Voyager probes, now far beyond the orbit of Neptune and travelling toward interstellar space, operate in conditions that no spacecraft has faced before. Their continued operation is a triumph of engineering, yet they are slowly succumbing to the inexorable march of wear, radiation, and power loss. Future interstellar vessels designed to travel far beyond the Sun's influence will face these challenges on an even larger scale, magnified by time, distance, and the unknown environment of deep space. As we contemplate sending humans or instruments beyond our solar system, we must confront the sobering reality that fragility is an unavoidable aspect of space travel. Every surface, every material, every system must endure an environment that is fundamentally hostile, where even the smallest particle can carry the power to disrupt, damage, or destroy. The very act of moving through space at high speeds amplifies these dangers, turning seemingly insignificant dust into deadly projectiles. While human ingenuity has allowed us to build vessels that can survive for decades or explore distant worlds, the fragility of spacecraft underscores the limits of our current technologies. It challenges us to think not only about speed and propulsion, but also about resilience, protection, and the long-term sustainability of missions that venture into the true unknown. To achieve meaningful interstellar travel, engineers and scientists must develop new materials capable of withstanding constant bombardment, new shielding techniques to disperse energy from impacts, and autonomous systems capable of monitoring, repairing, and reinforcing structural integrity over decades or centuries. Research into self-healing materials, advanced composites, and robotic maintenance systems is already underway, but the scale of the challenge remains immense. Fragility is not merely a technical problem. It is a fundamental consequence of physics, material science, and the nature of the universe. Every additional year in space increases exposure to hazards, magnifying the risk and testing the limits of our ingenuity. The journey from the solar system to the stars will be measured not only in light years, but also in the capacity of human technology to endure the relentless assault of time, radiation, and the countless microscopic collisions that constitute the harsh reality of interstellar travel. Even as we dream of spacecraft that can travel to distant stars, the fragility of these vessels reminds us that the cosmos is not a passive environment waiting to be explored. Space is filled with energetic particles, invisible debris, temperature extremes, and forces that relentlessly act on every material we send into it. Any long-term mission must account for this fragility in every detail, from the composition of alloys and polymers to the design of protective shielding, the redundancy of critical systems, and the strategies for autonomous repair. The smallest flaw, the tiniest crack, or the slightest unprotected surface can become the starting point for catastrophic failure over the course of decades or centuries. In this sense, the fragility of spacecraft is not just a technical limitation, it is a fundamental barrier that defines the outer limits of human exploration and the challenges we must overcome if we are to leave the protective confines of our solar system and reach for the stars. Fragility also interacts with another profound problem: the time required for interstellar travel. A journey to even the nearest star, Alpha Centauri, at a fraction of the speed of light, might take decades, if not centuries. This extended duration magnifies every aspect of wear and damage. What might be a minor abrasion or tiny puncture in the first few years could expand, compound, and become critical over decades of exposure. Material fatigue, microcracks, erosion from high-speed particles, and cumulative radiation damage all grow inexorably with time. Unlike terrestrial engineering, where maintenance, repair, and replacement are readily available, a spacecraft on a centuries-long mission must be designed to endure this entire period autonomously, with systems robust enough to resist failure from countless tiny assaults that accumulate relentlessly. The design of interstellar vessels must therefore embrace principles of extreme durability. Every component must account for cumulative effects, tolerances must be exceptionally tight, and safety margins must be far larger than anything currently used in Earthbound or near-Earth missions. Structural components may need to be layered, with sacrificial outer shells absorbing impacts while inner layers remain intact. Electronics may require multiple redundancies and radiation-hardened circuits. Life support systems, if human crews are involved, must incorporate multiple backups and autonomous repair capabilities. Propulsion systems must be designed to resist not only material fatigue but also erosion from particle impacts. Even communication systems must account for the gradual degradation of antennas and transmission surfaces over time. The fragility of spacecraft, therefore, imposes a holistic constraint. influencing every aspect of design, from materials to mechanics, from shielding to system architecture. The concept of human space travel has always carried a weight of imagination and ambition, pushing the boundaries of what we consider possible. We have sent probes to the edges of our solar system, rovers to the surfaces of distant planets, and orbiters to study the faintest glimmers of light from stars hundreds of light years away. Yet, when we consider the next monumental leap for humanity, travelling to another star system, the challenges become both immense and deeply human. One of the most significant of these challenges is the simple yet profound reality of time, and how it interacts with the human biological clock, shaping what it would mean to undertake a mission that spans multiple generations. Unlike a journey to the Moon or even Mars, interstellar travel is measured not in days or months but in decades, centuries, or even millennia. The human lifespan, which typically stretches just a little past 70 or 80 years, is short in comparison to these cosmic distances. This discrepancy forces us to confront an uncomfortable truth. Missions to stars beyond our sun cannot be completed by a single crew unless we somehow radically extend human life or develop technology that moves faster than anything we currently imagine. As a result, the idea of generational missions arises, a voyage in which the original astronauts begin the journey, but their descendants, born and raised aboard the spacecraft, are the ones to reach the destination. While this concept might sound like a natural evolution of human spacefaring ambition, it is fraught with ethical, biological, psychological, and logistical challenges, each of which must be considered carefully if humanity is ever to become an interstellar species. At its core, a generational mission confronts the basic rhythm of human life, the biological clock that governs growth, development, and reproduction. Every human being is subject to the same cycle: birth, growth, maturation, reproduction, aging, and death. Our biology has evolved to function within the confines of the Earth's environment, with gravity, radiation levels, atmospheric composition, and day-night cycles calibrated to our physiology. When we remove humans from this context and place them in the isolated and artificial environment of a spacecraft travelling for decades or centuries, this biological clock continues to tick, but it now does so under extreme conditions that our bodies were never designed to withstand. Growth and development in microgravity, exposure to cosmic radiation, limited genetic diversity, and the stresses of social confinement can all alter or impair these natural processes. A child born on such a mission would experience a very different childhood from one on Earth, not just socially but biologically. Their bones would grow weaker without consistent gravity, their muscles would atrophy without normal exercise, and their immune systems could be compromised by long-term exposure to radiation that penetrates the thin shielding of a spacecraft. These physiological realities are not minor inconveniences. They shape the very possibility of sustaining life over multiple generations. Reproduction, in particular, becomes a central concern. On Earth, humans have evolved reproductive strategies finely tuned to environmental conditions. Fertility, gestation, and childbirth are all influenced by nutrition, stress levels, hormonal balance, and physical health. In a spacecraft, these factors are artificially maintained, but not perfectly. Microgravity affects the development of reproductive organs, potentially altering fertility rates over successive generations. Nutritional deficiencies, even minor ones, could accumulate and lead to genetic or epigenetic effects that compromise health in descendants. Furthermore, the very act of pregnancy in microgravity presents unknown risks. Blood flow, organ positioning, and the distribution of bodily fluids behave differently when gravity is reduced or absent, which could result in complications that humanity has never encountered before. These risks amplify across generations. If one generation suffers compromised health, their offspring may inherit not only genetic issues but also weakened physiological adaptations, creating a downward spiral that threatens the long-term viability of the mission. Beyond the purely biological, there is the question of ethics. A generational mission requires that humans be born into circumstances they did not choose. The first crew members agree to a long, difficult journey with the understanding that they are making a conscious decision. But their children, born aboard the spacecraft, have no choice in the matter. They are confined to an artificial habitat, isolated from the diversity of ecosystems, societies, and cultures that define life on Earth. They will grow up never feeling the warmth of natural sunlight, never breathing the wind over the ocean, never experiencing the vast forests, mountains, or deserts that shape human development and imagination. The ethical question is profound. Is it justifiable to create lives that are bound to a purpose not of their own making, with the sole goal of reaching a distant star system? Can the needs, desires, and autonomy of these future generations be subordinated to the ambitions of their ancestors? Philosophers, ethicists, and futurists have debated this question extensively, yet no consensus exists. It challenges the very idea of consent and human rights. If one generation imposes a destiny on the next, does the mission remain an achievement of human ingenuity, or does it become a form of intergenerational coercion? The logistical difficulties compound these ethical dilemmas. Sustaining life for a single human over decades is challenging enough, but for multiple generations it becomes a task of staggering complexity. Food, water, oxygen, waste recycling, and medical care must all be maintained indefinitely. Closed ecological systems must be created, capable of generating not just sustenance, but a stable, life-supporting environment. Scientists have experimented with miniature models of such systems on Earth, like the BIOS 3 project in Russia or the more recent experiments in sealed habitat modules, but scaling these systems for hundreds of people over centuries introduces uncertainties that are difficult to predict. Even small failures, crop diseases, microbial contamination, mechanical breakdowns, could cascade into catastrophic shortages. Maintaining genetic diversity adds another layer of complexity. To prevent inbreeding and preserve the long-term health of the crew, careful management of reproduction and genetic exchange must be enforced, raising ethical questions about freedom and reproductive choice. Who decides when and with whom one may reproduce? How much control over the private lives of generations can the mission planners ethically exercise? These questions are not theoretical. They are operational constraints that would directly affect the design and management of any generational spacecraft. Psychological and social factors present additional hurdles. Humans are social creatures, and our mental health depends heavily on variety, novelty, and connection to broader cultural and environmental contexts. A closed spacecraft is inherently limited in these dimensions. Generations raised in isolation may experience social stress, psychological disorders, and a stunted sense of identity if cultural, educational, and recreational resources are insufficiently diverse. Over time, the shared mission purpose may fade as descendants forget the original vision of their ancestors. Cultural drift could occur, creating new norms, languages, and social structures that diverge from those of Earth. Leadership succession, governance, conflict resolution, and education must all be carefully planned, but even the most detailed protocols cannot fully predict the ways human communities will evolve in a self-contained environment over decades. The mental resilience of generations becomes as critical as their physical health. One of the most scientifically intriguing aspects of generational missions is the interaction between human biology and artificial environments across time. Microgravity has well-documented effects on the human body. Bones lose calcium, muscles weaken, the heart adapts to pumping blood in less gravitational resistance, and sensory perception shifts. While these changes are partially reversible when returning to Earth, on a spacecraft designed for centuries of travel, there is no return. Over generations, humans might evolve or adapt physiologically to life in low gravity, potentially creating a population that is no longer compatible with Earth's environment. Radiation, another constant hazard, further complicates matters. Cosmic rays and solar radiation are far more intense beyond Earth's protective magnetosphere, and even the thickest shielding cannot fully eliminate exposure. DNA damage, cancer risk, and long-term cellular degeneration are all likely to increase with each successive generation, possibly accelerating aging or impairing reproduction. Scientists theorize that epigenetic changes, modifications in gene expression caused by environmental stresses, could accumulate, subtly reshaping human physiology over hundreds of years. These adaptations might allow survival in space, but at the cost of a connection to the biology of our ancestral home. Energy and propulsion considerations also intersect with the human factor in generational missions. Because these journeys are measured in decades or centuries, the spacecraft cannot rely solely on conventional chemical rockets. which exhaust fuel long before the mission is completed. Alternative propulsion methods, such as nuclear thermal propulsion, ion drives, or even theoretical fusion-based engines, offer higher efficiency but require complex engineering and maintenance. A generational mission implies a self-sustaining system. Engines, life support, communication arrays, and navigation systems must remain operational far beyond the lifespans of any individual crew member. Maintenance crews and engineers must be trained from birth to operate and repair systems they did not create. Knowledge transfer across generations becomes critical. A lapse in understanding or skill could compromise the mission entirely. In this way, the biological clock of the humans on board is intertwined with the technological clock of the spacecraft. Each depends on the other for survival and progress. Cultural continuity is another subtle yet profound challenge. The story and purpose of the mission must be passed down, not as legend or myth, but as practical knowledge that sustains cooperation and morale. Children born on the spacecraft must understand not only how to operate complex systems, but why these tasks matter. Education becomes both technical and philosophical. Crew members must learn mathematics, physics, biology, engineering, and problem-solving skills, alongside ethical reasoning, leadership, and social cooperation. Storytelling, cultural preservation, and emotional support are essential for maintaining motivation. Without these elements, the mission risks not just physical failure, but the collapse of the social structure that makes collective effort possible. Generational missions require a civilization encapsulated within a ship, one where every member understands the delicate balance between individual needs and collective survival. Historical analogies, while imperfect, help illuminate these challenges. Human colonies on Earth have struggled to maintain population health and cultural cohesion in isolated environments. Early settlements in harsh climates, remote islands, and polar regions often faced high mortality rates, disease, famine, and social conflict. Even in modern times, long-duration isolation experiments, such as those conducted in Antarctica or in submarine crews, reveal the psychological strain of confinement, monotony, and separation from the wider human community. Extrapolating these lessons to a generational spacecraft magnifies the stakes by orders of magnitude. The crew has no escape, no resupply, and no external assistance. Every aspect of life must be anticipated and maintained over time spans that stretch beyond the human imagination. The spacecraft itself becomes not merely a vehicle, but an entire ecosystem, a closed world in which the biological clock of its inhabitants sets the pace of survival, adaptation, and evolution. Ethical considerations, however, continue to loom over the practical ones. Even if science and engineering can solve the technical problems of a multi-generational journey, the moral implications remain difficult to reconcile. Is it ethical to mandate that future generations be born into a life of confinement and labour for a purpose chosen by their ancestors? Could alternative approaches such as suspended animation or life extension offer a morally superior solution by allowing the original crew to reach the destination without forcing successive generations into service? If life extension technologies advance to the point where humans can live several centuries, the idea of generational missions might be rendered obsolete, but until then, the dilemma persists. The ethics of choice, autonomy, and consent are entwined with the very feasibility of these missions, creating a tension between human ambition and human dignity. Despite these challenges, the scientific and philosophical allure of generational missions remains powerful. They compel humanity to confront questions about who we are, what we value, and how far we are willing to go to explore the cosmos. The endeavour touches on biology, physics, psychology, sociology, and ethics simultaneously. It forces us to think not just about technology, but about the very essence of human life, its fragility, adaptability, and social complexity. The spacecraft becomes a microcosm of civilization, a test of our ability to preserve knowledge, maintain cooperation, and nurture life under extreme conditions. In studying the possibility of generational missions, we learn more about ourselves than about the stars we hope to reach. We understand the limits of our bodies, the resilience of our minds, and the delicate balance between individual rights and collective goals. Even if such missions never leave Earth, the thought experiments, simulations, and research they inspire enrich our understanding of biology, ecology, and the human condition. Scientific research into multi-generational spaceflight continues to explore these dimensions. Experiments with rotating space habitats, hydroponic agriculture, artificial ecosystems, and radiation shielding provide insights into what life might be like aboard a ship, traveling to the nearest star systems. Computer models simulate population dynamics, genetic diversity, and social evolution over hundreds of years, revealing potential pitfalls and strategies for survival. NASA, the European Space Agency, and private space ventures consider these questions in the context of long-term missions to Mars, which, while not generational in the same sense, provide a testing ground for life support systems, crew selection, and psychological resilience. Each experiment and simulation informs our understanding of what would be necessary to sustain human life across multiple generations in the harsh void of interstellar space. Ultimately, the concept of generational missions highlights the extraordinary interplay between the human biological clock and the cosmic timescales that define the universe. While a rocket can travel at tens of thousands of kilometers per hour, and probes can cross billions of kilometers over decades, the human lifespan remains a narrow constraint. This mismatch forces us to confront not only technological challenges, but the deep ethical and existential questions that arise when our species attempts to reach beyond its natural limits. Generational missions are a testament to both the audacity and fragility of human ambition, revealing that the journey to the stars is not merely a question of physics or engineering, but of life itself, of how fragile and precious human existence truly is. The idea of humans living on Mars has captured the imagination of generations, fueled by movies, books, and a seemingly endless stream of media headlines. The concept is simple: humans leaving the confines of Earth to settle on another world, building colonies beneath the red sky, and venturing across alien landscapes. It sounds heroic, exciting, and even inevitable, as if our destiny in the universe is written across the stars. Yet, behind the allure and cinematic visions, the reality of establishing human life on Mars is staggeringly complex, far harsher, and far more dangerous than most people realize. Popular culture often paints a picture of a barren, dusty desert, with a few high-tech buildings, a few spacesuits walking on the surface, and humans thriving on the so-called red planet. In truth, the conditions on Mars are extraordinarily hostile, presenting challenges that strain the limits of human biology, technology, and imagination. First, the environment itself is fundamentally alien. Mars is not just a cold desert, it is a world of extremes. The atmosphere is over 96% carbon dioxide, with almost no oxygen to breathe, meaning humans cannot survive without airtight habitats and continuous oxygen supply. The atmospheric pressure is less than 1% of Earth's at sea level, making the very act of breathing impossible without life support. Temperatures vary drastically, swinging from an average of about -80 degrees Fahrenheit, which is roughly -67 degrees Celsius, to daytime highs near the equator of just 20 degrees Fahrenheit, or around -7 degrees Celsius. At night, temperatures can plummet even further, reaching hundreds of degrees below the freezing point of water. Any human exposed without proper protection would not just freeze, but would also suffer from bodily fluids beginning to boil at such low pressure, a phenomenon known as ebulism. Popular images of people casually walking on Mars fail to convey the lethal cold that permeates the planet and seeps into even the most insulated habitats if they are poorly designed. Another major hazard comes from the very soil that covers the Martian surface. While Earth's soil is a living ecosystem of microbes, nutrients, and minerals that support agriculture, Martian regolith is fundamentally different. The soil contains highly reactive chemicals, including perchlorates, which are chlorine-based compounds toxic to humans. Perchlorates can interfere with thyroid function and other metabolic processes if ingested or inhaled, meaning that even growing food in Martian soil is far more complicated than planting seeds. It is not enough to just bring a few sacks of earth soil or rely on the local dirt. Every crop would require careful treatment, including the removal or neutralization of toxic chemicals, controlled irrigation with purified water, and supplementation with nutrients completely absent in the Martian soil. Furthermore, the soil is extremely fine and powdery, akin to a combination of talcum powder and volcanic ash, and it clings to everything. This fine dust penetrates seals, joints, machinery, and even spacesuits, threatening life support systems and clogging mechanical components. A single, sustained dust intrusion could disable critical equipment, turning a routine day into a life-threatening emergency. Mars is also notorious for its dust storms, some of which engulf the entire planet and last for weeks or even months. Unlike the brief, localized dust storms on Earth, Martian storms can cover the planet from pole to pole, reducing visibility to zero and blocking sunlight completely. For colonies dependent on solar energy, this is a catastrophic problem, as panels would cease to generate electricity for weeks, leaving habitats reliant on backup power and potentially dwindling supplies of life-sustaining resources. The winds themselves, though thinner than Earth's due to the low atmospheric pressure, can carry dust with enough momentum to erode exposed surfaces and damage sensitive instruments over time. Imagine an entire planet covered in fine, corrosive dust that penetrates every crevice of a habitat, slowly wearing down metal, rubber, and electronics. This is not a temporary inconvenience, but a constant, ever-present threat. Water, one of the most fundamental necessities for life, is also scarce on Mars. While there is evidence of frozen water at the poles and subsurface ice, it is not readily accessible. Extracting usable water requires significant energy to melt ice or chemically liberate water molecules from minerals, a process that is far more complex and energy-intensive than simply tapping into a lake or river as on Earth. Every drop of water would need to be carefully recycled and protected from contamination. Even minimal leaks in plumbing could have catastrophic consequences, potentially depriving settlers of their most precious resource. Without abundant and reliable water, growing food, generating oxygen, and maintaining hygiene would all become monumental challenges. Gravity on Mars presents yet another subtle but profound challenge. At just 38% of Earth's gravity, the long-term effects on the human body are uncertain. We know from decades of studying astronauts in microgravity aboard space stations that bone density and muscle mass decline rapidly without the constant pull of gravity. On Mars, these processes may be slower than in zero gravity, but still significant enough to pose health risks. The cardiovascular system, skeletal structure, and even vision may be affected over time, making long-term habitation potentially dangerous. Unlike astronauts on short missions, settlers would face years of adaptation, with the possibility that human bodies might weaken or suffer chronic conditions simply from living in reduced gravity. Radiation is one of the most insidious threats for Martian colonists. Mars lacks a global magnetic field like Earth's, which protects us from cosmic rays and solar radiation. On Earth, we are shielded by both the magnetosphere and the thick atmosphere, but on Mars, radiation penetrates deeply into habitats and through protective suits. Over time, this exposure increases the risk of cancer, neurological disorders, and genetic damage. For long-term settlers, even the best shielding technologies may provide only partial protection, forcing colonies to bury habitats beneath meters of soil or ice to reduce radiation levels. Living underground is feasible, but dramatically complicates construction, transportation, and communication, creating a constant trade-off between safety and practicality. In addition to these physical hazards, the logistical challenges of supporting a human colony are staggering. Earth is more than 55 million kilometers away at its closest approach, and most resupply missions would take months to reach Mars. Even the fastest spacecraft we can currently build would need several months to cross this distance under ideal conditions, meaning that settlers would need to be almost entirely self-sufficient. Any failure in life support systems, agriculture, or energy generation could have catastrophic consequences before a rescue mission could arrive. Colonists would effectively be living on an isolated island in the solar system, completely dependent on their own ingenuity, planning, and ability to maintain complex systems indefinitely. Transporting humans and supplies to Mars is itself a monumental undertaking. Every kilogram of material sent from Earth requires enormous amounts of fuel and energy, creating a limit on what can be feasibly transported. Habitats, machinery, and food must be compact, robust, and multifunctional, as there is no luxury of redundancy or spare parts like on Earth. Spacesuits, which on Earth are already complex life support systems in themselves, would need to function perfectly under harsh conditions for extended periods, with failures potentially resulting in instant death. The psychological burden of living in such confined, dangerous, and alien conditions cannot be underestimated. Humans are social creatures, but isolation, lack of variety, constant stress, and the knowledge of being so far from home could lead to mental health crises, making psychological support as important as physical life support. Popular culture often portrays Mars as a barren, silent desert with only minor challenges, but the reality is that every element of survival, from oxygen and food to energy and shelter, is a delicate, interconnected system. One failure can cascade into multiple crises. For instance, a blocked water filtration system could prevent both drinking water and agricultural irrigation, which would in turn reduce oxygen generation in plant-based life support systems. A dust storm could knock out solar power, leaving backup batteries depleted, while a malfunctioning heating system in extreme cold could freeze water pipes and life support machinery. Unlike Earth, there is no emergency services system to call or neighbouring community to provide help. Settlers must anticipate and solve every problem themselves, often in conditions that are physically punishing, mentally exhausting, and technologically unforgiving. Even the seemingly simple act of construction on Mars is fraught with difficulty. Building habitats requires protection against radiation, insulation against extreme cold, and airtight seals to prevent the thin atmosphere from venting inside. Traditional Earth construction techniques do not translate to Mars, and every building material must either be transported at great expense or sourced from local regolith in ways that remain largely experimental. 3D printing with Martian soil has been proposed, but the technology is in its infancy, and scaling it to provide robust, safe and livable habitats for large numbers of humans is far from certain. Add to this the need for airlocks, pressure regulation systems, and dust mitigation, and the process of creating even a small settlement becomes a monumental engineering problem. Despite decades of speculation and planning, the timeline for a viable Mars colony remains uncertain. While private companies and national space agencies have proposed ambitious goals, such as sending humans to Mars within the next 2 decades, these timelines often assume ideal conditions, rapid technological breakthroughs, and unprecedented levels of funding and international cooperation. In reality, each challenge, from radiation to dust storms, water extraction, and long-term human health, is a field of research still in progress, and each requires solutions that are not just effective but also reliable under extreme conditions. The difference between short-term visits, where astronauts can endure hardships for weeks or months, and long-term settlement, where humans must thrive for years or decades, is vast. Temporary missions allow risk tolerance and redundancy that are unacceptable for a permanent colony. Moreover, human biology itself may impose limits that technology cannot easily overcome. Fertility, reproduction, and healthy child development in low-gravity and high-radiation environments are unknown factors. Embryonic development, organ growth, and even genetic stability could be adversely affected, meaning that colonists may face challenges in sustaining populations beyond a single generation. Medical emergencies, which on Earth can often be treated quickly, become critical and potentially fatal in the Martian context, as there are no nearby hospitals or specialists. Every illness, injury, or congenital condition becomes a test of survival, demanding unprecedented levels of preparation, skill, and resilience. Even communication with Earth presents subtle but important difficulties. Signals take between 3 and 22 minutes to travel one way, depending on the relative positions of Mars and Earth. This delay makes real-time guidance or remote control impossible, forcing settlers to operate autonomously. Every decision, from repairing a life support system to responding to medical emergencies, must be made independently, without immediate backup. Psychological stress, high stakes, and the absence of real-time support amplify the dangers of every routine task, creating a constant pressure that is difficult to fully grasp from afar. All of these factors combine to create what can be called the Mars illusion. Popular culture, with its sleek visuals, adventurous narratives, and optimistic timelines, underrepresents the deadly complexity of establishing human life on the planet. The illusion suggests that Mars is merely a challenge of engineering and exploration, solvable with enough effort and ingenuity. In reality, it is a hostile world, where every step outside a habitat is a gamble, every dust storm is a potential catastrophe, and every system must function flawlessly under extreme conditions. The romanticism of living on the red planet masks the harsh reality. Mars is not just another Earth-like world, it is a place fundamentally alien to human life, where survival requires constant vigilance, adaptation, and technological mastery. The allure of Mars is undeniable, But it is important to recognize that fascination alone cannot overcome the inherent dangers. Colonization is not just a matter of landing humans on the surface. It is a test of human endurance, technological innovation, and societal resilience on a scale never before attempted. While Mars may one day host humans, it will not be a casual endeavor. The planet's extreme cold, toxic soil, reduced gravity, punishing radiation, scarce water, relentless dust and isolation create a reality that is far removed from the sanitized, adventurous images often portrayed in the media. Each problem interlocks with the next, creating a fragile ecosystem of survival where one failure can cascade into multiple crises. Unlike exploration on Earth, where humans can adapt, evacuate, or call for help, Mars offers no margin for error. The dream of humans living permanently in space, building colonies on distant worlds, or travelling to other stars is one that has captured the imagination of our species for decades. Yet, behind the bold ideas of space stations, interplanetary bases, and even starships capable of reaching nearby solar systems, lies a problem that is deeply personal and biological. The question of whether humans can even reproduce outside of Earth. The process of human reproduction, which on Earth seems almost automatic and natural, relies on a delicate balance of gravity, radiation levels, chemical signals, and environmental conditions that our bodies have evolved with over millions of years. When we consider the possibility of living in zero gravity, on a space station, on the Moon, or on Mars, we immediately encounter a biological landscape that is hostile to the continuation of our species. Fertility may be disrupted, pregnancies may become dangerous or impossible, and the development of infants may be radically impaired in ways that challenge our understanding of biology. The deeper we study these questions, the more we realize that the problem of sustaining human reproduction in space is not simply a matter of technology or engineering. It is a profound challenge at the very core of what makes us human. Human fertility is a complex process that depends on precise hormonal cycles, the production of viable eggs and sperm, and the ability of these reproductive cells to meet and fuse successfully. On Earth, these processes are finely tuned to the natural rhythm of gravity, the Earth's magnetic field, day and night cycles, and environmental factors that have shaped our evolution. In a zero-gravity environment, the body experiences significant changes. Research on astronauts has shown that even short periods in microgravity can lead to changes in the cardiovascular system, bone density, and muscle mass. It seems likely that these same stresses could affect reproductive organs and processes. The testes and ovaries, for example, rely on proper blood flow and hormonal signaling to function normally. In zero gravity, fluids in the body shift upward toward the head, causing a range of physical changes such as facial swelling, pressure on the eyes, and alterations in intracranial pressure. These shifts may also alter the function of reproductive organs in ways that we do not fully understand. For men, sperm motility, the ability of sperm to swim properly toward an egg, may be affected by the absence of gravity. Sperm are already microscopic, delicate cells, and their ability to navigate the fluid environment of the female reproductive tract could be significantly impaired in a microgravity environment. For women, the complex interplay of hormones that regulates ovulation and prepares the uterus for pregnancy could be disrupted, leading to irregular cycles or the inability to carry a pregnancy to term. Radiation presents another profound challenge. Beyond the protective shield of Earth's atmosphere and magnetic field, humans are exposed to cosmic rays and solar radiation at levels far higher than anything experienced on Earth. These forms of radiation can damage DNA, the blueprint of life, in both reproductive cells and developing embryos. On Earth, our environment naturally shields us from the vast majority of harmful radiation, and our cells have evolved mechanisms to repair minor DNA damage. In space, however, these mechanisms are overwhelmed by constant exposure. Sperm and eggs, with their unique chromosomal structures, are particularly sensitive to radiation. Even small amounts of damage can render them incapable of fertilization, or, if fertilization occurs, may lead to severe developmental defects in embryos. For a woman carrying a pregnancy in space, the situation is even more dire. Radiation can cause mutations in rapidly dividing embryonic cells, disrupt the formation of organs, and increase the risk of miscarriage. Studies using animal models, including rodents and amphibians, have shown that exposure to space radiation can significantly reduce fertility and lead to high rates of developmental abnormalities in offspring. Extrapolating these results to humans suggests that sustaining healthy pregnancies in space may require unprecedented levels of protection against radiation, far beyond current technology. Even if conception were possible in space, pregnancy itself would pose extraordinary challenges. On Earth, the force of gravity plays a crucial role in the development of the fetus. Gravity influences blood flow, the distribution of fluids in the mother's body, and the physical orientation of the growing baby. In zero gravity, blood does not circulate in the same way, the heart may work harder to pump blood, and the uterus may not maintain the correct shape and orientation for proper fetal development. Bones and muscles in the fetus, which rely on resistance to gravity to develop properly, may not grow as expected. The skeletal system in particular is highly sensitive to mechanical stress, and a fetus growing in microgravity may develop weaker bones or abnormal bone structures. Additionally, the vestibular system, which governs balance and spatial orientation, develops in the womb under the constant influence of gravity. In microgravity, this system may develop incorrectly, leading to potential lifelong challenges in movement and coordination. The placenta, the lifeline between mother and fetus, may also be affected by altered blood flow and fluid distribution, threatening the delivery of oxygen and nutrients essential for fetal growth. Infant development does not end at birth. Even if a child were successfully delivered in space, the postnatal environment presents new obstacles. Gravity is critical for many physiological processes, including circulation, lung function, and musculoskeletal development. Infants rely on gravity to learn to hold their heads up, crawl, walk, and coordinate movements. Without this stimulus, motor development could be severely delayed or abnormal. The immune system, which develops in response to environmental cues and microbial exposure, may also be impaired in space. Microgravity alters the function of immune cells, reducing their ability to respond to infections. Infants born in space may therefore be highly vulnerable to diseases and infections that would be relatively minor on Earth. Nutrition adds another layer of difficulty. Human milk composition is influenced by maternal physiology, and the ability of a mother to produce sufficient nutritious milk in zero gravity is uncertain. Feeding methods that rely on gravity, such as bottle feeding, may need to be re-engineered entirely, while ensuring sanitation and preventing contamination becomes even more critical in a closed environment like a spacecraft or space station. The social and psychological aspects of reproduction in space are no less important. Human reproduction is not only a biological process but also a social one, influenced by emotional bonds, stress levels, and environmental stability. Living in confined spaces for extended periods, under constant surveillance, and in a high-stress environment such as deep space, may impair the natural processes that support healthy reproduction. Stress hormones like cortisol are known to interfere with fertility, ovulation, and sperm quality. Chronic stress, which is almost inevitable in long-term space missions, could further reduce the likelihood of successful conception and pregnancy. Moreover, raising a child in an artificial, isolated environment, where social interaction is limited and sensory stimuli are unnatural, could have profound effects on cognitive, emotional, and social development. Children born in space may experience delays or impairments in learning, communication, and emotional regulation, presenting challenges for their survival and integration into a human community. From a technological perspective, the idea of supporting reproduction in space requires innovations that are currently beyond our reach. Shielding against radiation must be far more effective than any spacecraft or habitat we currently possess. Artificial gravity, whether generated by rotation or other means, may be necessary to simulate the forces that guide development from conception to birth. Life support systems would need to maintain highly stable environments for temperature, humidity, oxygen levels, and nutrition, tailored to the needs of pregnant women and developing infants. Medical interventions from prenatal care to emergency obstetrics would need to be entirely reimagined for space conditions where traditional hospitals and medical infrastructure cannot exist. Even basic procedures such as cesarean sections or neonatal resuscitation become complex and risky in microgravity, requiring specialized equipment, training, and protocols. Ethical questions further complicate the issue. Sending humans on missions where reproduction is uncertain or potentially dangerous raises serious moral concerns. Is it ethical to bring a child into an environment where their development may be compromised, their lifespan threatened, or their quality of life severely diminished? What rights do spaceborne humans have, and how do we ensure their welfare in a setting far removed from Earth? These questions extend beyond individual choices to collective responsibility, especially if the goal is to establish permanent human colonies on other planets or in deep space. The scientific community is just beginning to grapple with these dilemmas, and they underscore the reality that space colonization is not simply an engineering challenge, but a profound biological and ethical one. Research into animal reproduction in space has provided some insights. The results have often been sobering. Experiments with rodents, fish, amphibians, and even insects have revealed that microgravity affects mating behavior, fertilization, embryonic development, and postnatal growth. Some species have managed to reproduce successfully, but many experience higher rates of miscarriage, developmental abnormalities, or failure to survive beyond early life stages. For mammals with complex reproductive systems similar to humans, these challenges are particularly pronounced. Studies aboard the International Space Station and previous missions have shown that mammalian embryos exposed to microgravity during critical stages of development exhibit abnormalities in cell division, tissue formation, and organ development. These findings suggest that human reproduction may be extremely difficult, if not impossible, without significant technological intervention to simulate Earth-like conditions. The challenges extend to genetic stability as well. In space, the combination of radiation, altered gravity, and environmental stress could accelerate mutations and genetic drift. Over multiple generations, this could lead to unforeseen consequences for the human gene pool, potentially producing traits that are maladaptive or harmful. Maintaining genetic diversity in a small space population becomes a major concern, as isolated colonies may lack the large gene pools necessary to prevent inbreeding and preserve healthy reproduction. Technologies such as sperm and egg banks, in vitro fertilization, and genetic monitoring may help mitigate some risks, but they introduce new complexities and dependencies on advanced scientific infrastructure that must function flawlessly in extreme environments. Even with all technological solutions in place, there is no guarantee that human reproduction in space could ever replicate the natural processes found on Earth. Gravity, radiation, magnetic fields, day-night cycles, social interactions, and environmental cues all play subtle but critical roles in fertility, pregnancy, and child development. Removing humans from these conditions disrupts an intricate web of biological and psychological factors honed over millions of years of evolution. While humans may survive in space with life support systems, and even thrive for limited periods, reproducing successfully and sustaining a multi-generational population presents challenges that go beyond our current understanding and capability. It is a stark reminder that space is not simply another place to live. It is an alien environment that resists our most intimate biological processes. The universe, as vast as it is, stretches far beyond the imagination, and yet within this enormous expanse, humans have always looked outward, searching for worlds that might resemble our own. The idea of planets outside our solar system, planets orbiting other stars known as exoplanets, has fascinated scientists and dreamers alike. For decades, we've imagined that among the billions of stars in the Milky Way galaxy, some must host planets with conditions suitable for life. We have developed powerful telescopes and observatories, such as the Hubble Space Telescope, the Kepler Space Telescope, and the Transiting Exoplanet Survey Satellite, to scan the night sky in search of these elusive worlds. By observing tiny dips in starlight when a planet crosses in front of its host star, or by detecting the faint wobble of a star caused by an orbiting planet's gravity, astronomers have discovered thousands of exoplanets, and among them, a smaller subset appears to fall within what scientists call the habitable zone, a region around a star where temperatures might allow liquid water to exist on a planet's surface. At first glance, this discovery seems promising. It suggests that humanity might one day find a second Earth, a distant world where life could potentially thrive, or even where humans might establish colonies. Some of the nearest known exoplanets that appear to be in their star's habitable zone include planets orbiting the star Proxima Centauri, which is roughly 4 light-years away from Earth, and planets around the star TRAPPIST-1, located about 39 light-years away. These distances, though vast, seem almost within reach in the imagination, particularly when compared with other stars in the galaxy that are tens of thousands of light years away. Yet, despite the allure of these nearby candidates, the reality is far more sobering. Even the planets closest to us may be completely inaccessible to human travellers, and even if reached, they may be utterly inhospitable to life as we know it. One of the first and most obvious barriers is sheer distance. The nearest exoplanetary system, Proxima Centauri, lies 4 light-years away. A light-year, the distance light travels in a year, measures almost 6 trillion miles. To put that in perspective, our fastest spacecraft to date, such as the Parker Solar Probe or the Voyager probes, travel only tens of thousands of miles per hour. Even if a spacecraft were somehow capable of sustaining a constant speed without stopping for decades, centuries, or even millennia, the journey to Proxima Centauri would still take thousands of years. Current human technology cannot close this gap in any meaningful time frame. To make interstellar travel feasible, we would need propulsion systems orders of magnitude more powerful than anything we currently possess. Concepts such as nuclear fusion drives, antimatter engines, or light sail technologies using massive laser arrays have been proposed in scientific literature, but all remain theoretical or at best in the early experimental stage. None of these technologies can yet propel a vessel to even a significant fraction of light speed, the speed necessary to reach nearby stars within a human lifetime. Even if the technical challenge of propulsion could be overcome, another obstacle arises: the fragile nature of spacecraft themselves. Spacecraft travelling across interstellar distances would face constant bombardment from cosmic dust, micrometeoroids, and high-energy radiation from stars and supernovae. At speeds approaching a significant fraction of the speed of light, even particles a fraction of an inch in size could cause catastrophic damage. Shielding a spacecraft against these impacts is a massive engineering challenge. Traditional metals like aluminum or titanium are inadequate for these conditions. Advanced materials, perhaps layered composites, electromagnetic deflectors, or even artificial magnetic fields would be required, but their feasibility over decades or centuries of continuous travel remains purely speculative. The universe is not a friendly place. Even a tiny mistake in shielding, navigation, or life support could doom an interstellar mission before it reaches its target. Beyond the technical and engineering challenges, the conditions on many exoplanets that appear to be in the habitable zone are themselves likely to be extremely hostile. A planet's location within the habitable zone is a necessary but not sufficient condition for life. Many factors can render a world uninhabitable, even if it lies at the right distance from its star. The composition of the atmosphere, for example, is crucial. If an exoplanet has a dense atmosphere dominated by carbon dioxide and lacking oxygen, life as we know it would be impossible without extensive technological intervention. Some exoplanets might have extreme surface temperatures, either scorching hot due to a runaway greenhouse effect or freezing cold if they lack an atmosphere that can retain heat. Many of the nearby red dwarf stars, such as Proxima Centauri and TRAPPIST-1, are notorious for their violent stellar activity. These small stars often emit intense flares of ultraviolet and X-ray radiation, far exceeding anything experienced on Earth. Such radiation could strip away a planet's atmosphere entirely, leaving it as a barren rock, incapable of supporting liquid water or life. In addition, the gravitational environment of a planet can complicate matters. Some exoplanets orbit so close to their stars that they are tidally locked, meaning one side of the planet permanently faces the star, while the other side remains in eternal darkness. This creates extreme temperature gradients, with the day side potentially boiling under constant stellar radiation and the night side frozen solid. While some models suggest that life might exist in a narrow band along the terminator, the region between day and night, the challenges of surviving in such an environment would be monumental. Human habitation would require enormous technological support, including artificial climate control, radiation shielding, and sustainable life support systems capable of operating in these extreme conditions for years, if not generations. Even planets with seemingly Earth-like conditions may harbour other invisible hazards. Toxic chemicals, lack of essential nutrients, or unstable geology could all make life support untenable. Volcanic activity, extreme storms, and unpredictable climate patterns could pose severe risks to any settlement. Moreover, the very concept of habitability, as scientists currently define it, is based on life as we understand it, meaning carbon-based organisms that require water and moderate temperatures. it is entirely possible that life elsewhere, if it exists, could follow radically different biochemical rules, rendering our assumptions about habitability incomplete or misleading. The ethical and logistical implications of attempting interstellar travel or colonization also cannot be ignored. Even if a habitable exoplanet were discovered, launching a multi-generational mission to reach it would involve committing countless lives to an uncertain fate. Generational ships where crews would live and die in transit would require precise management of food, water, air, and energy over centuries. Reproduction and human health in such environments are poorly understood. Microgravity or artificial gravity systems, exposure to cosmic radiation, and psychological stresses of isolation over multiple generations could all result in profound physiological and mental challenges. Essentially, reaching even a nearby exoplanet may require humanity to rewrite the very rules of survival and society. On top of these challenges, the cosmic neighborhood itself presents hazards. The space between stars is not empty. It contains diffuse gas, cosmic rays, and magnetic fields that can affect navigation and communication. Spacecraft traveling for decades or centuries may drift off course due to tiny gravitational perturbations from passing stars or interstellar gas clouds. Maintaining precise trajectory over such timescales is almost inconceivably difficult. Even if the spacecraft arrives at its target, decades of isolation and time dilation effects, predicted by Einstein's theory of relativity for near-light speed travel, could mean that the crew arrives to a world that has changed, or even to a galaxy subtly different from the one they left. Communication with Earth, separated by light years, would also be delayed, making any form of real-time guidance impossible. In addition, the discovery of exoplanets does not guarantee that they can be explored or colonized in a way that preserves human life. Our current detection methods, transits, radial velocity, and direct imaging provide only limited information. We can estimate a planet's size, its distance from its star, and some atmospheric characteristics, but we cannot yet determine surface conditions, magnetic fields, ocean chemistry, or the presence of life. Many exoplanets discovered in the habitable zone might be false positives for habitability. They may be worlds with thick, crushing atmospheres, extreme pressure, or poisonous elements. Some may be dry, airless rocks, despite receiving the right amount of starlight to allow liquid water under ideal conditions. Without sending probes or actually landing on these worlds, we cannot know for certain whether they are truly habitable. Even sending robotic probes presents challenges. A probe travelling at a fraction of light speed designed to reach the nearest potentially habitable planet would still take decades or centuries to arrive. Protecting its electronics and sensors against cosmic rays and micrometeoroids over such a long journey is a formidable engineering challenge. Ensuring that it can transmit data back to Earth across light years of distance, without losing signal or suffering from interference, requires breakthroughs in communication technology that have not yet been realized. In essence, our ability to explore these distant worlds is still in its infancy. The dream of interstellar exploration, while exciting, remains far beyond our current technological reach. Moreover, the interstellar neighborhood may be even less forgiving than it appears. Many stars are surrounded by debris disks, asteroid belts, or clouds of interstellar dust. A spacecraft approaching a distant system could encounter unexpected hazards, such as high-speed dust grains capable of penetrating armor, or gravitational interactions with undetected planets that could alter its trajectory. Even if the spacecraft survives the journey, the target planet itself might not be stationary. Planetary orbits can evolve over millions of years, and conditions that once seemed favorable may change due to stellar evolution, orbital instabilities, or catastrophic events such as nearby supernova explosions. One of the most obvious and persistent barriers is propulsion. Moving anything through space is not like driving a car on a road. In space, there is no air to push against, no friction to help slow you down, and nothing to carry you along except the fuel and engines you bring with you. The universe operates under strict physical laws, and one of the most important of these is Newton's third law. For every action, there is an equal and opposite reaction. Spacecraft propulsion works on this principle. To move forward, a spacecraft must push something backward. Rockets on Earth do this by burning fuel, creating high-speed exhaust gases that are expelled from the engine nozzle. The reaction propels the rocket forward. While this principle is simple, The practical application is extremely complicated. Rockets are enormously inefficient. To reach even a tiny fraction of the speed of light, which is the ultimate goal if humanity ever wants to travel to other star systems, the amount of fuel required grows exponentially. It is not a linear problem. Each additional increase in velocity requires an exponentially larger amount of fuel. This is known in physics as the rocket equation, formulated by the Russian scientist Konstantin Tsiolkovsky more than 100 years ago. The rocket equation mathematically demonstrates that to reach speeds approaching even 10% of the speed of light, a spacecraft would need to carry fuel in amounts that are effectively impossible. A spaceship designed to reach a distant star at such speeds could easily end up being mostly fuel, leaving almost no room for crew, equipment, or supplies. Scientists have proposed several ideas to overcome this problem. Nuclear propulsion is one of the most discussed concepts. Nuclear thermal rockets, for instance, would heat hydrogen using nuclear reactions to generate thrust far more efficiently than chemical rockets. Nuclear pulse propulsion, a concept studied in the United States in the mid-20th century under a program called Project Orion, would literally explode nuclear bombs behind a spacecraft to push it forward. In theory, these methods could reach speeds high enough to travel between stars within a human lifetime. However, these ideas face staggering engineering, political, and safety challenges. Launching nuclear devices into space is extremely risky, and containing the energy of nuclear explosions to safely propel a spacecraft without destroying it remains unsolved. More speculative proposals, such as antimatter propulsion or light sails powered by giant lasers, promise even faster travel, potentially up to significant fractions of light speed. Yet, antimatter is extraordinarily difficult to produce and store. Creating even a few grams of antimatter would take decades of continuous operation in the most advanced particle accelerators and would cost far more than the total annual budget of all space agencies combined. Storing antimatter safely for years without it coming into contact with normal matter and causing a catastrophic explosion is a problem that currently has no feasible solution. Light sails, meanwhile, require lasers with immense and precise energy output, focused over distances of thousands of kilometers, which our current technology cannot sustain. Even if these barriers were overcome, reaching another star system in less than a human lifetime remains an almost unimaginable challenge. Even if propulsion challenges were solved, another barrier arises: the limits of materials science. Space is not gentle. Any spacecraft leaving the solar system must survive extreme conditions for decades or even centuries. Temperatures in space vary from hundreds of degrees below zero in the shadow of planets to thousands of degrees in direct sunlight near stars. Cosmic radiation, solar storms, and high-energy particles can gradually degrade the materials of a spacecraft. Even tiny micrometeoroids traveling at tens of kilometers per second can punch through hulls, destroy electronics, or release lethal clouds of debris. The materials required to build a spacecraft that can survive these conditions for centuries do not currently exist. Metals fatigue, composites crack, and even the most advanced ceramics can only withstand so much repeated stress before failure. Scientists have explored theoretical materials like carbon nanotubes or graphene composites, which could, in principle, offer remarkable strength-to-weight ratios. Yet, producing these materials at the scale needed for an interstellar spacecraft is far beyond our current capabilities, and even these supermaterials may have unknown vulnerabilities when subjected to decades of cosmic radiation. Life support systems present perhaps the most human of all barriers. Even if a spacecraft can travel safely and materials can withstand the harshness of space, humans themselves are fragile and vulnerable. Life support systems are incredibly complex, requiring the continuous management of air, water, food, and waste for years or decades. The International Space Station, one of humanity's most advanced habitats in space, already struggles to maintain stable conditions for months at a time. The idea of extending this to decades or centuries is almost unimaginable. Air must be continuously purified of carbon dioxide and other contaminants. Oxygen must be replenished, water recycled, and food grown or stored for multiple generations. Small failures in these systems can lead to catastrophic outcomes. Bacteria, fungi, and other microorganisms can colonize closed systems and damage critical equipment, or compromise food and water supplies. The biological effects of long-term space travel on humans are still poorly understood. Microgravity leads to muscle atrophy, bone density loss, and changes in cardiovascular health. Cosmic radiation increases the risk of cancer and can cause irreversible genetic damage. Long-term isolation and confinement can lead to severe psychological effects, including depression, anxiety, and behavioral disorders. Creating a self-sustaining environment capable of supporting humans for generations is not simply an engineering challenge. It is an almost philosophical problem, as it requires replicating the delicate balance of Earth's ecosystems inside a spacecraft. Another consideration often overlooked is the scale of time required for interstellar travel. Even if a spacecraft could reach 10% of the speed of light, a speed currently far beyond practical engineering, it would still take more than 40 years to reach the nearest star system, Proxima Centauri, which is approximately 4.2 light-years away. That is a generation of humans living, aging, and dying entirely inside a spaceship. If propulsion was slower, travel could take centuries or millennia. In such scenarios, missions would need to be multi-generational, with humans reproducing and dying on board. This introduces an entirely new set of biological and ethical problems. Can humans survive and remain healthy over multiple generations in an artificial closed environment? Can we maintain genetic diversity to prevent inbreeding and disease? How do we address the psychological challenges of being born into a ship that will never see Earth again? Even if these problems could theoretically be solved, the social and moral consequences are profound and have no precedent in human history. The interstellar environment itself presents additional limits. Space is not empty. It is filled with radiation, dust, and particles moving at tremendous speeds. Even a tiny particle, moving at a significant fraction of light speed, can release energy equivalent to a large bomb upon impact. A spacecraft traveling at such speeds would have to navigate a gauntlet of potential collisions, with no chance to stop or maneuver quickly. Shielding against such hazards requires enormous mass, which in turn requires even more fuel to accelerate, a vicious cycle that feeds back into the propulsion problem. This demonstrates a fundamental tension. The faster a spacecraft goes, the more energy it requires, and the more vulnerable it becomes to hazards that it might otherwise avoid at slower speeds. There may simply be a natural speed limit for human interstellar travel imposed by the physics of high-speed collisions in space. Even communications pose limits. A spacecraft traveling light-years away would be separated from Earth by enormous distances. Sending a simple message would take years, decades, or centuries to arrive, and any response would take just as long. This introduces a problem of isolation and uncertainty that humans are not naturally equipped to handle. Coordinating a mission, solving unforeseen problems, or receiving guidance from Earth would be impossible in real time. A crew would be entirely self-reliant, without any possibility of rescue or external support, placing extraordinary demands on their problem-solving skills and autonomy.